Okay, but anyway, we will be talking about health inequality, health equity, and there will be some kind of practical applications. I know some of you are with your laptops. Who has data here? Okay, good. Even if you don't, you're going to follow. I'll give you a link to all the materials, all the data sets, all the codes, all the programs, whatever it is. You will see it. I tried a bit to do a little bit of data programming for you so that you have pretty much like a flair of how to now manipulate data sets. You can build on the data program, edit it, make it yours, and it's going to work for you. Especially for decomposition, because if you're familiar with the decomposition you have for health inequality, most of them you cannot generate standard errors, okay? So I tried to program such that you can bootstrap and generate your own standard errors, and you can edit them. I'll provide all of them to you in a while. So when we talk of health inequalities, well, we all know that health inequalities are pretty much differences in health. That's all. But beyond that, what are health inequalities? It's important to know that when we talk about health inequalities, we're not just interested in the fact that there will be inequalities. Let me give you a case. For example, we know that incomes will always be unequal. Whatever we do, incomes will always be unequal. Is that why we should be worried? Or are we worried because incomes are not related to people's skills? Or are we worried because incomes are not equal? Then we begin to fight government that, hey, that lady that is a medical doctor is earning more than I cleaning the floor. So should we be worried about differences in income for the sake of the fact that they are different, or because they are not tied to our abilities and skills? You now realize that our focus is not necessarily that incomes are unequal, which there will always be, unless we all have the same skills. The whole, everything is equal, but we don't all have equal training. Some people have PhDs, some have masters, some have undergraduates. So by that, we should expect that incomes should be different. So the fact that we see income inequality is not just something we should begin to shout about, that incomes are unequal, but incomes are unequal if a man and a woman who have the same skills are not getting the same income. Then that's a problem. Not because we figured out that everyone's income, oh, your income is not the same as mine, we begin to shout and like, oh, we need incomes to be equal, okay? So that's the kind of mindset that we should have approaching inequalities in health as well. But health is so interesting in the sense that we all need good health. It's not like income where people have abilities, others don't have abilities. We all, as a matter of fact, merit good health, okay? So differences in health, whether it's morbidity, mortality or morbidity, health status, and also access to health services are things that we are interested in between individuals and population groups. There can be absolute inequalities, and there could also be relative inequalities. Absolute inequality is basically the one that tells us that this person has more health insurance coverage than I do. That's absolute. More health insurance coverage because he has access to more generous plans that gives him access, cover that gives him access to maybe treatment abroad, and I may not have it. So that in itself is inequality at the absolute level. Now, relativity is the fact that when you compare people who should pretty much have, when you compare somebody to what the average health of a population is, for example, then you're looking at relative to somebody else who is the average person in a community or society. You might look at two classes of inequality measures that, like I said, one compares a group of individuals with another group or another individual's health or a population health average. Or you might just compare me to everyone else, like I did. And you can nest that in whether it's an absolute measure or a relative measure. But my interest here, I would submit quickly, is that we are focusing on what economists call socioeconomic inequalities in health, which basically measures the joint distribution between socioeconomic status and health or ill health, health outcomes, health status. health insurance coverage, whatever you might want to call it. Then there is also the discussion around the social determinants of health that we will touch on a bit. This is going to be more of an introductory kind of teaching or seminar or whatever you want to call it. We'll have follow-up to this at maybe any of our AFIA programs, which will roll out in a couple of months. So the social determinants of health inequalities. We know that many of the things that determine health don't sit within the health sector, many of them. For example, think for a minute, malaria. Many countries suffer a lot from malaria. But you will realize in a while that malaria is caused mainly by failure in the environmental sector, not the health sector. People get bitten by mosquitoes because they breed in ponds that are left pretty much on waters that don't flow. And those kind of grounds are breeding grounds for mosquitoes. And mosquitoes end up infecting people with malaria, and people end up in the hospital or health sector. Now, the health sector deals with that, which could have been handled from the environment sector. Same with road accidents. Road accidents has a lot to do with traffic department, whatever you want to call it in your country. If roads are not well built, people end up either dying or seriously injured, and they end up where? In the hospital. You can think of many, many, many other things. TB, for example, has a lot to do with the environment. Either working conditions or wherever you work, and then exposure to what gives you TB, and you end up in the hospital. So many, many things are not necessarily the fault of the health sector. But the health sector, I would usually call it a residual sector. It just sits with the ills of many other sectors. And that's where the social determinants of health is very important. That many of these factors impact on health inequalities. And we need to understand these factors and how they play in pretty much determining inequalities in health. The major sectors that have been identified by the Commission on the Social Determinants of Health include schooling or education, employment, not just employment, employment quality, income and poverty, environment and sanitation. I've talked a lot about how clean your environment needs to be and sanitation. We know a lot with diarrhea, for example. Diarrhea is something that can be handled, again, not caused by the health sector, but the health sector suffers a lot. If the water is clean, if there's clean water supply, hygiene, the health sector wouldn't suffer. So you realize that majority, if not 90% of what the health sector deals with can be handled outside the health sector. And the health sector would have been dealing with conditions that are pretty much the non-communicable diseases that maybe hit you from something you don't know. So that's something important to keep in mind. Now, there are methods. I'm giving an overview, then we'll go into the practical session. We will touch on many of these things. There are methods that are used to assess health inequalities. And I draw this from the work of others, Wagstaff, Pachi, and Van Dosler. The range is one we all know, right from secondary school, pre-secondary or whatever. We've been doing range forever. It's just taking the one with the lowest value, the one with the highest value, and the difference between them gives us the range. That range is basically saying who is the sickest person, who is the healthiest person, the difference. It means nothing too much because we don't know what's in between. So it's a very difficult measure to explain. It overlooks what goes on in the middle. If you want to do the range by quintiles, you could say, well, this is the bottom, this is the top, and then the bottom quartile, and the top quartile, or the whatever you want to call it, decile. It's up to you. Some people use ratio, pretty much the same, depends on how you interpret it. It's simple to understand, but like I said, it's not something we should be looking at. It's something that was done in the late 70s and early 80s. Then the other one is the Lorenz curve. The Lorenz curve is originally from income distribution. It comes from income distribution in the sense that you could plot, we'll show in a while, you could plot, I'm sure you all know the Lorenz curve. Let me not preach to the choir. Do you all know the Lorenz curve? Before I begin to, okay, we don't all know. Okay, before I start preaching to the choir. The Lorenz curve is pretty much used originally as a measure to show income distribution, originally, income distribution. Because with the Lorenz curve, we can compute the Gini index. You've all heard about the Gini index of income inequality. The Gini index of income inequality is just a summary measure from the Lorenz curve. Now, the Lorenz curve has two axes. On the vertical axis, you pretty much accumulate people's income, the share of their income, okay? So you could have 10%, 15%, blah, 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 to 100%. Then you rank people. It doesn't matter how you rank them, but for neatness, for a well-behaved curve, you basically rank people from the lowest person to the highest, but you don't need to, the Lorenz curve, just for the curve to be neat. So if you rank people in that order, what you're now saying is that you want to take the bottom X% of population, the bottom 10% of population. What is their share of income? So if the bottom 10% of population account for 10% of incomes, then you're now dealing with a straight line. The bottom 20% account for 20% of incomes, the bottom 50%, 50% of income, 90%, 90% of the income. Then you have what we call a 45-degree line that measures line of equality, which means everyone gets their share of income, but we know that never happens, okay? But everyone gets their share of income. So if I get 50% of population and I ask them their income, I should be able to get 50% of the income in that country by virtue of the fact that we're dealing with equality. But unfortunately, we fall short of equality. So what that means is that you find out that the bottom 20% of population might sit with 5% of income in the country. The bottom 70% might sit with 20% of the income in the country. That is the inequality we're measuring with the Lorenz curve. But applying it to measuring health is slightly different and hard to interpret, very hard to interpret. What that means is that you rank people from poorest health to best health. Try and figure out how you can rank people from the most feeble person to the strongest person. I don't know how you can rank that. But if you can rank them by the weakest person to the strongest person, and then you are basically measuring what proportion of health does the bottom 5% of population have, and what blah, 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 blah. It's not very nice. It's not very nice. You would see quickly that it's difficult to even explain the context of the weakest person to the strongest person. So usually I don't even want to look at it. So, but at least you understand the concept from income inequality. Then the other one is the Gini coefficient, which is a summary measure of the Lorenz curve. So I wouldn't talk much about it. It just basically measures, it's a ratio. It's a ratio of areas. It's just a ratio of areas. Usually it is, depending on how you, when you draw the curve, I wish I could shade the curve for you. Then we'll show you the area that measures the Gini index. Now, the Gini index or Gini coefficient can never be negative, can always be positive, as opposed to the concentration index, which we've seen a while, because it can only happen in one plane, in just one quadrant. It all happen in one quadrant, but in one plane, the toppermost plane. It can never go below the line of equality. So it cannot go above the line of equality. So when you draw the Lorenz curve can never go above the line of equality. And that's the reason why, one of the reasons why the Gini index can never be negative. But with the concentration curve, it may go up or down. And that gives it a way in terms of whether it can be positive or negative. And also it has implications for the values. The Gini index ranges from 0 to 1. 0 means perfect equality. 1 is the worst. The highest level of inequality you can ever think about is the Gini index of 1. And what that means is that only the strongest person in the rest are dead, but it doesn't happen. So it's only one person that has all the health, all the good health. I don't know how I can interpret that. Then the rest are pretty much dead. But intuitively, that's what it means. But I don't know how that is possible. So you may not get a 0 if you use the Gini index for, 1 if you get the Gini index, if you want to use the Gini index to measure health inequalities. Then the other one is index of dissimilarities, which borrows a lot from information theory. Now, what this does is that what you're trying to measure is pretty much gap. You're summing up the gap. So you're assuming that every population should have their own population share of health. So depending on how you group people, you might, in this case, if you're interested in socioeconomic status, you might group people by socioeconomic groups, the poorest quintile, the blah, 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 to the richest quintile. So for each quintile or each group, you have their share of health and their share in the entire population. For example, if you are using quintile, the poorest quintile might have 10% of the share of health, but their share of population is 20% because it's a 20% in terms of quintiles. So this difference is what you're interested in. So you will quickly see how this takes its sign, whether it's positive or negative. It's just from here. If the share of health is less than your share of population, it quickly takes a negative sign. If you see how that plays out, then it's the sum of it. But the problem is that things can cancel out. One negative from one group can cancel another positive. So you don't even know what's playing out. You don't know what's playing out. So you end up getting a value that is positive, but there could be many, many negatives, but only one large positive dominating that and then giving you an ID that is positive. So what does that mean? Okay. So usually it's something that we really don't use, but it's very simple to compute. This again does not necessarily link, like I'm saying, linking this to socioeconomic status, no matter how hard you try to use the groups of SES to do this. Like I said, you don't know what's playing out. Anything can generate a positive or negative. Then the interesting ones that we're going to solve here, one is the slope index of income, of inequality, not income. The slope index of inequality is a very simple one, a very, very simple one. It's just saying, literally, rank people from the, you can do this by income. Rank people from the poorest to the richest, and then fit a regression line. That's all, simple. Just fit a regression line. The regression line will tell you whether it's positive or negative slope. If you understand how regression lines work, a positive or negative slope. And if it's a positive slope, it means that there's a positive relationship between income or socioeconomic status and health status. And if it's a negative slope, it means that income and health are moving in opposite direction. The richer you are, the poorer. The richer you are, the sicker you are. The richer you are, well, it depends on what measure of health you take, okay? I must always quickly highlight that. So it depends on, if the measure of health I take is poor health, then you interpret it accordingly. But if it is good health, you interpret it accordingly. Depending on what the measure is, very important, what measure of health you take, but they will move in opposite direction if it's a negative slope. But we don't necessarily just use people ranked in that way. We use what we call a fractional rank. Fractional rank is a different kind of rank. It's similar to the raw rank, but is slightly different because it allows you to move away from the boundaries, the extreme boundaries that distort things. I'll show you in a while. And you don't worry about it. We'll talk about many of these. And then related to that is what we call the relative index of inequality. The relative index of inequality is pretty much the same as the slope index. The slope index is the slope when you fit that line. You know, remember your usual mathematics, you get a slope value. That slope value is the measure of the slope index. All you need to do to make it relative is divide it by the average health in that population. So to move from absolute to relative, all you need to do is divide. When you have an absolute value, you divide by the mean health of the population. You've moved from the realm of absolute to relative. The same with the concentration index. We also have an absolute concentration index. We rarely use it, but it's very much there. So that's what that does. The beauty of that is that this allows you to also do socioeconomic related inequalities, not so much with the slope index, but with the relative index. The slope index is sensitive to scale. It's sensitive to scale in the sense that if I double, and that's the same problem with absolute measures. If I double people's health, my slope index will change, but the relative index remains the same. If it's like what you call a monotonic transformation. You monotonically transform the value such that you multiply by the same scalar, positive value, and everyone's health improves. The relative measure would not change, but the absolute measure will change. So that's the difference between an absolute measure and the relative measure, is how responsive the measure is to any positive monotonic transformation of people's health. Now, the other one, last one I'll talk about is the concentration curve. The concentration curve is similar to the Lorenz curve. The only difference here is that the concentration curve, you must rank people from the poorest to the richest. You don't need to do that for the Lorenz curve, but for a neat curve. But for the concentration curve, you must do that. So when you rank people from the poorest to the richest, you're trying to say the poorest X% of population, what is their share of health? The bottom Y% of population, what is their share of health? I'm going to show you all this. I'm pretty much taking you through. It's like a practical 101 course, but let's do a quick rundown of theory. Then we see it in real life. It's usually very difficult to start practical, and people have not had a refresher of this. So we compute this loosely as twice the area between the concentration curve, which you'll see in a while, and a line of equality, which we usually call the 45-degree line. I will show you how the 45-degree line comes about. This has a very good advantage in the sense that you can assess relative measures of, it's a relative measure of health inequality, and it does not necessarily deal with the extreme like we saw with the range. It's a value that summarizes a distribution along from 0 to 1. So it covers the entire population rather than two extreme groups. The weakness is that how do you tell a policymaker what the concentration index of 0.6 is? It's a big problem. How? What does it mean, 0.6? A policymaker sees your paper and says, well, your concentration index is 0.6. Is it 60%? No. What is it? You can't explain. Okay? I will talk about what to present to a policymaker in that regard in a while. So that's that about the measures. I'm happy to take questions on that before I now show you a bit of practicals. Happy to. This is pretty much an informal, and we're going to engage in a while. Yes.
Hello, my name is Shirisha. I'm from India. So, sir, I have used SII, slope index, as well as concentration index in one of my doctoral work. One of the challenges that I face is sometimes they move in opposite directions. The SII says that it is pro-rich distribution, while the CIX says it's more concentrated among the poor population. So that is one of the challenges I face. And another doubt I have is I don't know really well, but I just want to, I think you may know better that the SII value coefficients comes as insignificant if the sample size is small. I don't know if that is the case. So these two are my doubts.
Yeah, very good question. Yeah. While you move there, let me quickly. The reason why it's strange why they should move in the opposite directions, because I can recompute the concentration index from the slope, from the slope as well as the relative index, because they all share the same similarities. You're dealing with covariances, but it could be that in your data they were not significant. I don't know. It could be that they were not significant. If they are not significant, we shouldn't be talking about them, because the beauty of statistics, with non-significance, it means that it could have been 0.1, could have been minus 0.9. That's why it's not significant, because you can't place where it is. After repeated sampling, it's unable to generate where it lies, so it just says it's 0. It doesn't really matter. Yeah. That's the beauty of statistics. I wish I could show you. There's something I always like teaching when I want to do stats 101 is the power of the normal curve. The power of the normal curve. It looks very simple, but when you see the power of the normal curve, you quickly realize that many things follow that normal distribution. You can easily draw samples and show how the normal curve can be built, because it's basically a sampling distribution of means, and usually follows the normal curve. And when you max your sample size, it's easily done. Yes.
My name is Iyab Watson from Ghana.
Yes.
Please, so we have indicated so many measures of inequality, and then you've also explained their weaknesses. So which one is preferred?
Very good question. I would say that no one is technically preferred, but depends on what you want. If you want to measure socioeconomic related inequalities, you cannot use any other one but the last two, which are the slope index and its associated relative index, and this. So these two are the ones that can be used to measure relative inequalities and socioeconomic related inequalities. Yes. Yes, some authors, like she said, some authors show both of them at the same time, but I have preference for this. But like I said, you can give me the relative index and we can work on it to give you the concentration index, because they're all from the they have the same structure. Yeah. You will see in a while that some people use what they call the convenient regression to obtain the concentration curve index. And also that convenience regression can be gotten from that slope index. Remember, it's also a regression. So yeah, possible. Okay, so now let's see this thing we call concentration curve. Come on. Okay, good. Now let's see how the concentration curve is pretty much generated. I'm going to use a very simple example so that we don't get into a very big data set. We'll soon do a big data set in a while, but let's start. We're building a model. It's bit by bit. So now let's imagine we're able to get people in a particular country called country X. Okay, no, we're not naming any country X. And in this country X, we have been able to group them into the poorest 20%, the second, blah, 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 to the richest 20%. And we want to find out the share of malnourished children. Let me just use children or people. People, I think, is the easiest way to go about it. People. The share of malnourished people, whether adults or children or whatever, let's group them together for now. And we say that the bottom 20%, the poorest 20% of people in this country account for 36% of malnourished people. Does that make sense? So we're assuming that 36% of malnourished people in that country belong to the bottom 20% of the population. And only 5% of malnourished people belong to the richest 20%. That's the kind of distribution we have. Then we'll move to good health, whatever good health is. Don't ask me, okay? we'll talk about that, whether you use a self-assessed health or use a EQD or whatever you use. But let's imagine we now generate good health, whatever it is. Now, that good health, we figured out that about 37%, almost 40% of people with good health are in the richest quintile, compared to only 7% in the poorest quintile. So you quickly see the gradient here, that this pretty much is pro-poor. It's a bad pro-poor. That's why I put it in. It's not good, but it's pro-poor in the sense that it is more, it's something that you find frequently amongst households in impoverished communities, as opposed to impoverished households, as opposed to the other one that is pro-rich. It is biased towards the rich. This one is biased towards the poor. Hence this name, you see pro-poor, pro-rich. Where is it biased towards? Is it the rich? Then it's pro-rich. Is it the poor? Pro-poor. Simple. And if it is pro-rich, we know that the concentration index is going to be negative. So I computed that myself. You can compute it if you want to. It's very easy to compute. And then this is pro-poor because it has a negative concentration index, and you've seen that. Now, quickly take a look at this. This is a summary of this. A policymaker will understand this, but will not understand this. But the two are same. You see where we're going? Now you have two audiences. If you want to publish your paper, you can put this in. Your fellow academic will understand. But the guy who is the Minister of Health, if you give her this and tell her to act, will ask you, what is this? What is minus? Okay. Is it that 30% of my population not getting what? They don't understand what this is, but they would understand that they need to find a way of dealing with minority children in the poorest communities. That they can understand. But the two, this is a summary of that. That's a summary of that. Then the last one is the share of injury. Let's imagine for some reason, injury is so, it's like a random process, which it should be if all things are equal. If it's a random process, it doesn't look at face before you become injured, okay? And then you hit with injury. Then we figured out that injury is well distributed amongst the population. The bottom 20% of injuries, the richest 20% of injuries. In that case, the concentration index, 0. The measure, the conclusion is that it's equality. Is that not equal? Everyone, injury is happening to everyone. So it doesn't really matter who you are. It's all the same. Now we can plot this on a graph. Now to plot that on a graph, you see, this is the case of good health. You will see clearly that pretty much the same information I gave you, 37%, 7%. And you see that? That's the gradient. If you give this to a policymaker, she would understand. At least, it may not fully understand, but better than the index. The same here with malnutrition. You see, it's more amongst okay, this is a 37. I think this was 30 something. I can't remember. But now you see this is 5% and this is 36 or 37%. That gradient is a negative gradient. Okay, and then you see, oh, sorry, I've gone backward. You see for injuries, it's pretty much equal. That's equality, 20% each. This same information can also be plotted on a concentration curve. You see, there are many ways to represent the same information depending on who you want to present it to. So if you represent the same information, no difference on the concentration curve, this is exactly what you get. Now let me explain what the concentration curve is. Here, if you look at the red line is good health. So the bottom 20% of the population, you could see, with less than 20% of good health. The bottom 40% of the population with less than 40% of good health, as opposed to injuries, where the bottom 20% have 20% of injuries, the bottom, but that way, can you see that? That's why this is called the line of equality. Because the bottom X% of the population have the corresponding share of whatever it is. Good health, poverty, whatever you want to call it. That's what they have. And that's why this is a line of equality. Now, this is pro-poor because you figured out that the bottom 20% of the population end up with more than 20% of their share of malnutrition. That means it is more in eating into the poor than the rich. But this is pro-rich, and this is pro-poor. So the same information can be put in an index, curve, how do you call it, bar charts. So you choose who you want to present it to. So as health economists, we shouldn't be only targeting journals to publish in, but we should also think of who we can communicate our results to. Good. So have I been able to at least take you through 101 of basic health inequalities before going to some developments, some complications? Now, let's get academic in a while. I might lose some audience, but it's okay. We'll try as much as possible to get you to understand. How do we compute this index for those who are interested? Remember, I talked about area. Theoretically, this is how we compute it. So we rank people, like I said, from the poorest guy to the richest guy or lady or person in the country, the poorest person to the richest person. And then we assess what share of whatever our interest is. It could be malnutrition. It could be, like I said, good health or injury. What share of injury does the 50% of the population sit with? What share of injury does 90 or 80% of the population sit with? So that will give us this curve called the concentration curve. Then we compare that with the line of equality. That shaded area, twice that area is what we call the concentration curve. And that too is appearing there for some reason, which if you want to understand it quickly, this curve could have switched as well. So it could have been here or it could have been there, and it should be able to give us the same measure. The only difference is that one will be negative and one will be positive. So one way of doing it is that 2 can be changed. The weight can be changed. That 2 is a weighting scheme that can be changed. Sometimes somebody would say, well, I want to favor the poor more than the rich. Then we change that weight of 2. We change it. But that weight of 2 is always there because it gives equal weight to everyone, whether you are rich or poor. But some people will say, no, we have interest in the poor. And in the realm of what we call the extended concentration index, we can change that too. But now we're not dealing with extended concentration index, we're dealing with basic concentration index. So we don't change that too. We keep it as 2. But in the realm of extended, we change the 2 to something else higher than 2. Once we go above 2, we're favoring the poor more than the rich. If we go below 2, we're favoring the rich more than the poor. So keep that in mind for extended concentration index. But we don't just apply 2 or 3 directly because it has to be woven into the function that's woven into the distribution. So twice this area is a concentration index. Very simple, not difficult. But in reality, we don't compute it that way, okay? In reality, we compute it using an equation. So now we know if the index is positive, it's pro-rich. If the index is negative, it's pro-poor. I've shown you over and over again. So you're going to have information overload. Now, the issue is that in health economics, we sit a lot with binary variables. A lot with binary variables. And a recent, well, not so recent, more than 10, 15 years ago, a paper by the late Wagstaff showed that, remember when I gave you the index, that it could range from -1 to +1. But when you're dealing with binary variables, that range is not easily figured out to be -1 to +1. It depends a lot on the proportion or mean. Let's call it mean or proportion. Since the binary variable, it depends on the proportion of that variable. So whether it's going to range from 0 to 1, of course, because it's a proportion. So it depends on the mean of that variable or proportion. And as a result, in large samples, let's deal with large samples that are maybe above 30 or 50 or 100 or whatever, preferably larger, you will have the range to be between this and this, as opposed to -1 and 1. So it's going to depend on the mean of the variable. And that's a very powerful finding. So what that means is that for a binary variable, the concentration index applied like that is problematic or could be problematic. So 2 normalization schemes exist in the literature for binary variables. And I'm particular about binary variables because we encounter them a lot in health economics. One is what Wagstaff suggested. He said that we should just divide the CI, which is the concentration index, by this entity here, this guy. So we just divide it by 1 minus that mean there. And he gave a reason just to be able to bound it. That's all. Just figuring out what's the best way to bound the index between -1 and 1. But Erigius queried that approach that is kind of ad hoc. So he went through pretty much like axiom to figure out the best way to normalize the index. And his own approach for a binary variable is this. But his approach was generalized, not just for binary variables, but for categorical variables, okay? So it's pretty much that. So what this means is 4 times the mean of the health variable multiplied by this. So in a way, they are similar. It's just a scaling factor that is different. This is scaled by 1 over this. This is scaled by 4 multiplied by this. So they all have the same CI, which means technically they should have the same sign, if you know what that means. The sign is determined by this. This is not going to change the sign because this can never be greater than 1, okay? And this cannot be less than 0. So the sign will remain the same. The only thing that will vary is the magnitude. And the magnitude will vary depending on the mean of the variable. Simple, short. Okay, now let's see what that means in a while. But before we go there, I want you to get to understand something. when we see this, for example, the use of ART services in Ghana, for some reason I chose Ghana, do we think this is equitable?
I think it is hard to tell because the need in this group might vary and this distribution might be equitable.
Oh, interesting. He said it might not. So he's not even answering the question yes or no. So yeah, who else wants to go? I thought this is simple. Yes. I thought this is simple.
Is it an example of horizontal equity? Yes. If that way we look at it, it is equitable.
Good. So she's saying if we come in as someone who is interested in horizontal equity, meaning that equal treatment for equal need, then this is equitable. Okay. That's her submission. Who else wants to try? Yes, she wants to try.
It is not. I think it is not equal, but I cannot say that this is equitable or this is not equitable because you haven't control for any variables inside the measure.
Now she is submitting that I think it's similar to what he's saying. This group is similar, I think, that this is not, okay, someone's asking, can't tell on the chat, at least you've read it. So thanks for those joining online, that you can't tell that that's what the person is saying, and similar to what she is saying, because you've not controlled for anything, any other variable. Interesting, let's see. Let's figure all this out. And is this equitable? Now, can we now, this is the same distribution, remember 26 to 12? Same, the blue one or whatever the color is, don't ask me, might be colorblind. And the red, if you don't see under color. So now the red color is basically showing the distribution of people with HIV in the country. And then the blue, is that blue or magenta? What do you call that? Okay, good. I want to, light blue. Okay, good. Let me go with you. And the light blue is saying that the bottom 20%, sorry, it's not showing, but at least you could see this, the bottom 20% down to the, some reason this came there. So the bottom 20% of the population here have about 32% of HIV cases, while the richest 20% sit with only 5% of HIV cases. Now look at how much ART they use. Is this equitable? Aha, so we're complicating the model a bit. We started with a very simple model that anyone will be happy to say, oh, then it's good. Come on, well, we're doing well. ART services, the poor guys are using more than the rich. Let's just go home and rest. I mean, we've done great. The government official will be happy to just show this to people and not show the other one, because they want to show that they've been able to serve the poor more than the rich. But when you layer on it the other variable called need or other variables, whatever it's called, you quickly begin to, I can layer that with many other variables, and it changes. The conclusion changes as you layer them with variables. Now, what that means is the same thing we talk about equity. The equity is in the eye of the beholder. It's like beauty. It's just pretty much in the mind of the beholder. So you could come to equity with different connotations. So whatever connotation, you need to be able to justify why you think that's equitable and why it's not equitable. But clearly you could see here that if the share of people with HIV is 32% in the poorest quintile and they're having 26% of ART services, there is a problem somewhere. There is a problem somewhere. It's not, I wouldn't call that equitable in any way. Okay, and that brings us to the other aspect called fairness in inequality. So not just because there's inequality, but some inequalities are fair, some inequalities are not not fair at all, at all. So socioeconomic inequality does not necessarily show fairness in the health, how health services are distributed, for example. It could be health outcomes. We assess fairness based on relationship between use and need. At least there should be some correspondence between the two measures. Horizontal equity is one that someone mentioned, equal use for equal need. So people with the same need or capacity to benefit should receive the same treatment. So if you have the same need, why should you have different treatment? It's possible. Someone would say, well, you have the same need, I'm giving different treatment because of a background information that is relevant, but not explicitly seen in the need. I don't know if you understand what I'm trying to say. There are two people here with the same need, but one is coming from a poor background, and then the other one is not coming from a poor background, and you want to give services, you might favor the other one with a poor background over this other guy because of the other information you have, not just based on the need information. That's why I say you can complicate things as much as you want to. So for us to be able to assess inequity, we first of all need to see the distribution of population and also see the distribution of, for example, this is the case of use of antenatal care services. I've shown you for ARTs. Now let's see what happens with pregnancies. We know that if this is the proportion of women in the poorest quintile who are pregnant, and this is the proportion of the richest women who are pregnant, then the use of antenatal care services should, as a matter of fact, follow that distribution. But if it follows another distribution like we see here, where the use of antenatal care services is not really matching the need for antenatal care services, then there's a mismatch, which means this is not equitable. The use of antenatal care services in this context cannot be equitable because it's not following the distribution of pregnant women, for example. So just seeing the use of antenatal care services, like I showed earlier, you'll be tempted to just conclude that, well, it's good, poorer women are using antenatal care services than the rich, good policy, and you endorse it. But you still need to go further to close this gap, okay? You still need to close this gap. So it's important to keep in mind the difference between inequality and equity. Good. Then the other one measures, I'm giving a lot of measures, which we'll deal with. The other measure is the decomposition of health inequality. You're pretty much aware, many of you are aware of the Wagstaff's approach, et al.'s approach to decomposition, okay, correct? I would try and recap it. So we're going to deal with that framework. So that framework basically, first of all, computes a measure of inequality using the concentration index. And then it tries to explain that index. What are the socioeconomic factors? What are the social determining factors of that inequality measure? So you want to see the contributions of different factors. It could be factors that are related to the individual. It could be societal factors. It could be factors that even lie outside, like I say, outside the health sector that contribute to that health inequality. So you get the measure of health inequality, sorry. And then you look for the factors that explain it. You compute the elasticity of health with regards to the factor. This is an economic term we use in economics. Many of you are economists here, so I wouldn't be preaching to the choir. But usually when economists talk about elasticity, what they're trying to say is something related to slope. Something related to slope. You remember how something changes if one other thing changes. So elasticity is basically that, how two things move, whether they move in the same direction or the opposite direction. So for example, if I put in X, what happens to Y? So I want to see how Y responds to what I do to X. So if X is, I'm giving you a 5 milligram of whatever, a penicillin, what happens to Y? Y will be my outcome, whatever that outcome is. So I want to see how you respond to that X I gave you. That's basically what economists call elasticity, just in a very simple layperson's understanding. So how do health variables respond to the factors, age, sex, income, blah, blah, blah? How do health variables respond to changes in these other variables? That's what this is. And this is really a descriptive model. It doesn't really show, even though we're measuring how one thing responds to the other, it's not causality. So we're not saying that age causes that, by this percentage or whatever. It's purely descriptive, not causality. So the way it goes is that I'll just flag it for you. You have the concentration index, and then that index is equal to, you compute the concentration indices for each contributing factor. You multiply that by the elasticity I just told you about. And when you sum that up together, it should give you back the concentration index. The only thing that will be lacking is one bit, which we usually call the residual, the part that cannot be explained. But if the model is well, if you can do it well, put in all the variables that matter, then this kind of fizzles away. But if it doesn't, then this will remain. It's a part that you cannot explain. Sometimes there are some things that you cannot explain. So we put it as unexplained factors. So that's pretty much the Wagstaff's framework. The concentration index can be split into two parts. One is the unexplained and the explained. And the explained part is the product of the concentration index of each, the sum of the concentration index of each factor multiplied by the elasticity. That way, basically. So no equations, just at least you should be able to understand this very basic. Great. So any questions before? I hope we're doing well with time. What's the time? I'm not. Good. Any questions before? Okay, good. Now let's revisit this concentration index thing, especially normalization. Now there's a paper, if you're interested, you can quickly take a look. It's a recent paper that I wrote looking at the Wagstaff and Erega's decomposition and the problems in those. But unfortunately, these two indices are still used until now. As an editor, I sit with people submitting papers with pretty much the same indices that by the time we're done with this, you understand the problems inherent in those two normalization schemes, or whether it's Erega's or the Wagstaff's approach. I'll try to be simple so that you see the issues there. Now, this is a summary of the issues that you find with the two normalization schemes. So what this simulation does is very simple. You can do it simple. We're going to do something similar in Theta. We'll do it so you see it coming out. It's not me telling you that this will happen. So this is a very simple simulation that you can do. So what this does is that in a population, imagine government comes now and says, what I want to do is I want to start by helping the poorest and move gradually until I get to the richest person. Okay, let me repeat it again. I want to start by helping the poorest person and move gradually till I get to the richest person. Now, let's take, for example, that it is malnutrition. I want to first of all eliminate malnutrition amongst the poorest, and then they move systematically in a very simple way till I get to the richest person. What do you think should happen to the index? Intuitively, without even doing anything. What do you think should happen to the concentration index? Imagine it was negative. We saw the concentration index that was negative before. And now I'm helping the poorest. I'm eliminating amongst the poor before I get to the richest person. What do you think will happen to the index? Yeah, okay. Let's see.
Should move towards equality, towards zero.
Good. Should move towards zero, and if possible, even become positive. Okay. You know why that's so? Because by the time you finish with the poorest, then you're now left with the richest. It should be now pro-rich, because it's now only amongst the rich. It's no longer nowhere near the poor anymore. It's gone. Good. So that's where we're starting from. So now we take a population and we start that, and we are going to compute every time we eliminate the poorest person. We compute the concentration index until we get to the richest person. So now this is if the bottom X% of the population has H to be equal to 1 and the top has H to be equal to 0. Now this is the other way around. So what this means is that depending on what the variable is, like I always say, it's very hard one to tell, because with health, you could come to it from good health or bad health. So let me imagine that this is bad health. Which one will I use? Okay, good. Anyone, the conclusion is the same. So now let's take, for example, that this one is the bottom X% of population has H to be equal to 1. Let's take this now to be bad health, okay? That means the bottom X% of population has H to be 1. So here is where the richest, where the only the poorest guy has H is equal to 1, which means only the poorest guy has bad health, okay? Does that make sense now? I think let me start with that. So if only the poorest guy has bad health, what do you think the concentration index should be? -1, because that's the worst. That's the worst case scenario, because it's only the poorest guy that has the worst, bad health. The rest, the top guys have no issue with bad health. So the concentration index should be -1. Okay, let's see which one behaves. Now, if you look at this, the CI is the regional concentration index. It tells us it's -1. This one is Wagstaff's index, pretty good, -1. But Erigas is telling us there is no inequality. There is no inequality. Meanwhile, the poorest person has all the bad things. You can think about it. But Erigas index is saying there is no inequality, and don't bother about that distribution. You're good. Okay? Now let's move. Let's begin to move. Now we're now saying that, let's imagine again, since we're dealing with poor health, for some reason, we're now giving the richer people poor health. We're giving it to them like a bad person. Okay, we're going. So we're now giving to the bottom 20% of the population, we're giving them bad health. By implication, because we've given the bottom 20% of the population bad health, the standard concentration index will behave this way, because you're now moving towards the rich. You're now basically progressing towards the rich. So it's a very natural progression. You're progressing towards the rich. You're going, and you keep going until you get to the rich. You get here, Wagstaff tells you it doesn't really matter, so long as whether it's the bottom 10 or 50 or 90 or X% of the population, it will always remain -1. So in this case, for example, if the bottom 40% of the population has bad health, okay, and the top 60% has good health, it's still -1. It's the worst. It's still the worst distribution you can ever have. So every distribution that has the bottom X% of the population, whether it's one or, is the worst distribution. But we know that one distribution should be better than the other. I mean, if you go to a policymaker, you're applying that index, you say, well, these two distributions are the same. This country is the same as this country, in as much as only this, only this guy has all the bad health, and the bottom, that to that, is the same distribution. No, it can't be the same distribution. Okay, now let's go to the Erigas model. It's now telling us that the distribution started from being equal, and now it's even becoming more concentrated amongst the what? Poor. Okay? Meanwhile, you are going towards the rich. But now it's now going backwards towards more, it's becoming worse amongst the poor, as opposed to showing the other way. It should be going the other way, as opposed to going backward. I don't know whether you get where I'm going. So this quickly shows you the way that these indices don't behave alike. So what this tells us is, for the EC, which is the Erigas correction, there is no the worst inequality that we understand as -1. Remember, concentration index can only happen when the bottom 50% of the population have bad health and the top 50% have good health. That's the worst. That's the worst case scenario that you can get from the Erigas concentration, which doesn't make sense. Yeah, good. Now you see, it doesn't make sense, because it can only be the worst, and anything outside that is not bad. Again, this is a symmetry. If you understand the symmetry, it means that whether you're dealing with the bottom 20% having bad health is the same as the bottom 70% having bad health. That is a symmetry. So it means that a distribution where the bottom 20% of the population has bad health is the same as the population where the bottom 70%, and anything in between is better. Okay. Yeah. You get what I mean? And anything in between is better than the two that are equal. Okay. So it means, therefore, that if you run a regression in Ghana and I run a regression in Nigeria and I compute this index here and that person computes the index here and I'm busy telling you that this guy here is better than this guy, it may not be true. It may not be true, but I don't even know what's playing out. Whether this is playing out, this cannot be worse, this cannot be better. I mean, you don't even know what's playing out. That's the problem with this index. But this, irrespective of its ills, of it not falling in the bounds. If our worry is the bounds, then it's a different ball game. But if our interest is consistency in showing the relationship between income and ill health, this still performs better. So now the issue is, what do you want the index to show? Is it just to show an index that behaves by, is bounded, the final outcome is bounded and it behaves this way? Or the one that at least gives you the relationship you want, and then you can explain in terms of context that this is coming from a binary variable, okay? That the bounds may not, it's like working with, if you know the standard economics theory, we talk about linear probability models and probability logic, okay? It's pretty much something of that nature. So now that is, so I implore you, you can read more about this. If you scan that code, you pick up the paper, yes. Mike?
Yeah, thank you very much. Yeah, I must confess, I've read this paper. I didn't get it the way you explained now. It makes a lot more sense. And I get the problem you are trying to point out. So is your recommendation is that the best you can do is to use the original one? Because the appeal of the correction is that you are able to compare because it's bounded. And what you're saying is that that's basically useless. That's a false. That bounding is telling you something wrong, and you're comparing falsely.
Correct. That's a very valid point. If you I'm glad you say you read the paper. The issue is, like I say, it depends on what you want. If you're interested in, well, when something is bounded, it behaves well because you, like you said, it's standardized. Okay, but whether the standardization is doing is creating a problem or solving a problem is something that we also need to interrogate. So not just the fact that it is bounded is now easy to compare, but the bounding can be something that creates a problem. So if a bounding creates a problem, so you need to check the pervasiveness of the problem it creates vis-a-vis the one that is not bounded. And if you check the pervasiveness, which I quickly tried to show here, that this may not be bounded, but if you're comparing two distributions that in themselves are both binary, the fact that the means vary and with relative index has already built into its own distribution, the mean, as opposed to absolute. I wouldn't really worry so much about this, but provided, like I always say, you report this and say this is coming from a distribution with a mean X. This is coming from a distribution with mean Y. Then someone who is interpreting it will know that this is the concentration index, but it's coming from a distribution with a different mean compared to my mean. Then however you deal with it is a different ballgame. But here, you don't know what the means are. You're only now given two indices, Ghana, Nigeria. Which country is better? You say, oh, this is bad. Meanwhile, Nigeria is here, oh, Nigeria is better. But in reality, you know, not better. In that sense. So it's just important to keep that in mind, that inequality conclusions will diverge significantly depending on what normalization scheme you use. There is no right or wrong answer. So it's important that this is, for me, a very important point, that when you interpret the Ehrlich's index, don't interpret it as the concentration index because it is not the concentration index. I think it's important to keep that in mind. So don't ever say that the concentration index is this, so it is pro-poor, this is more pro-poor than the other, is more pro, because you don't know what is going on, basically. It's very difficult, but basically that's it. So you cannot interpret it the same way as you do to the standard concentration index. I'm sorry, because I've shown that progressive achievements when moving from the poorest to the rich will initially worsen socioeconomic inequalities using one, and then it starts improving when you reach 50% of the population again. So you have a mirror distribution. So the worst distribution is the one where 50% of the population has whatever X is or H is, which shouldn't be the worst distribution. The worst distribution is where the poorest person has that ill health. Only the poorest guy, not the bottom 50% of the population. It can't be the worst. It can never be the worst distribution of inequality you ever get. Good. So now the other issue that we need to also deal with, I worked on this quite a while ago again, is the seasonality. That ill health, like any other thing, even mental illness, has seasons. And there are peak seasons when people develop different kinds of illnesses. Malaria, even mental exam, if you're a student, exam period can be one. You can relate to that. Exam period can be really stressful and you develop it. So that period is like a cycle. Every time exam comes up, you have more mental health cases being reported to wellness clinics than usual. So now, knowing that, we now need to understand that when we compute inequality measures, we need to ensure that seasonality is built into it, especially if we're dealing with reported illnesses. Like, for example, we want to compute inequalities in malaria incidents. And we go to Ghana, we get a data set, data were collected in rainy season. And we know that's a peak period for malaria. Okay, now if you want to compute inequality index and you don't adjust, when you want to analyze that and you don't adjust for the fact that when the data were collected, it was a peak period, you inflate malaria incidence and then you distort inequality. You basically distort inequality. And I will show you how that plays out in a while. So that's what that paper also does. I said disease follow, blah, blah, blah. So socioeconomic inequalities need to analyze, need to adjust as much as possible. Socioeconomic inequalities in health. Let me do we have any time for Z3? For whatever I call it, break. Okay. And let me know when, okay, I'm still far off. But let me know if you need a break because I have been talking a lot. But I will give you a break, not too far from now. We'll break before we do the practicals. So yeah, we'll break. We're not going to this. We're going to do data codes. Beauty of it is that I've written them all for you. So we'll just run them out, explain what each code is doing. I did a little bit of programming within. So you can also apply the programming to Bootstrap, to do other technical, tough stuff, whatever you want to do. So now, when you do annualization, usually, if you know they collect outpatient service utilization, we usually use 4-week recall period or 2-week recall period. And for inpatient, we usually use 12 months, 1 year. The reason is because what happens frequently, you remember, but something that happens long time ago, you will struggle to remember. That's the whole idea behind that. So because these recall periods happen, and they come to your house and say, in the last 1 month, how many malaria cases have you recorded? And you only tell us maybe 0 because they only came during the time when malaria is not existent. And then you want to compute inequality, you will never get a good measure of inequality. Also, you will never get a good measure of annualized service utilization. So surveys that are conducted within a particular period of time are the kind of surveys that are problematic. However, if such surveys are done using diaries, okay, which is the new method of collecting data, and such diaries are given year-round, such that you exhaust the whole season, voila, you're good. But if the surveys are not kind of conducted such that you have an annual cycle, it's a problem when you want to annualize. And that's where the seasonality comes in because of the recall periods and stuff like that. So what? Okay, I'll skip this. Because again, the issue is that it misleads when you do cross-country comparison. I try to explain how that works because you're trying to compare Ghana with Morocco, for example. And maybe the seasons when data were collected were totally different seasons. And you're comparing apples with oranges and saying the malaria incidence is higher here than the other, might be even lower in Ghana than in Morocco. You're like, because of when it was data were collected. So it's very important to keep that in mind. Okay. I think it's thinking. Oh, I see I have overshot it now. Oh no. Let me go back. Takes a while to think and not sure why. Good. No, not yet. Tech group. I'm not sure why what I'm saying. Okay, I think this is where we are. So now this is the seasonality index. What a seasonality index does is a very simple, I like simple things. So don't worry, I talk a lot, but I like simple things. Now what this index does is that it just takes the numerator there sums up to do this, you need to have what we call the health management information system, for example, that has track of utilization data from January to December or May to April, or whatever your cycle is. So you already have annual utilization. So what you need to do is, what month did you conduct that survey? That month is the one that is at the bottom. Then the top is basically the summation of all the utilization from January to December or whatever. That's the top. So what you're trying to figure out is the index will give you how you can annualize your utilization such that it reflects the annual distribution, so that when you compute inequality index, you are computing a very good inequality index. And that came up because in many household surveys, you hear them say this survey was conducted between January and October. If you remember, go back and check your household surveys. They will tell you this was conducted between January and March or whatever, October. But that doesn't mean that maybe in a particular, the northern region, it was in January. In the middle region, it was March. In the whatever region, it was, but the whole survey was conducted between that. And then they lump up everything together and tell you, this is the result, this is the survey. There's a problem here, because the problem of seasonality is built in that data set. So you need to unpack it. You need to take out the seasonal variations, such that you can really compare apples with oranges. So apples to apples rather than apples with oranges. So that is what this index does. I wouldn't bore you into, but if you're interested, you can pick up the book, the paper to read more about it. So this is how the characterization would work, depending on how the seasonality works. The seasonality can either influence your final conclusion to move from pro-poor to pro-rich, can move it from pro-rich to pro-poor, can move it back to equality. So it's a very important thing to take into account. So I implemented this in South Africa. And implementing in South Africa, you see the results shown here. So you would see the one that does not include, if this can you see some significant changes in one that uses uniform annualization and the one that seasonally adjusts. You could find some significant changes, although not necessarily it's pretty much in the magnitude as opposed to the signs in this case. But that doesn't mean that it cannot happen otherwise in other contexts. So it's just the data set I could implement on basically. But the theoretical finding remains the same. Good. I hope you can take it now that this thing is appearing below. Let me try and adjust it so that this thing will shift up a bit, because we are going to break. What's the time? The break is 2. So we're almost there. Okay, good. We're going to break in the next. Can you scan it? Is it possible? Because it's broken. Does it work? Oh, good. Now, if you can access that, you get all the materials, including this presentation, including itself. You get the link to a Google Drive folder. Confirm? I just need to be sure. Okay, good. If one person confirms, then I know it should work for all of you. And if you cannot get a link, put in the short URL. You can easily type it. It takes you straight up to all the materials that we're going to use for a practical session. They said a lunch, not lunch, but the tea break will be served in 4 minutes or so. So if you want to download that on your computer or laptop or whatever, you can take your time now to do it before the and questions, bring them up. Yeah.
Yeah, just a quick question. I understand that econometrically or statistically, one of the reason why you would want to do the seasonality correction is because you're concerned about the correlation between seasonality and the outcome variable. Now, if you're doing cross-country comparisons, should you worry about these same type of issues also when it comes to the composition? For example, maybe the racial composition, racial ethnic composition across countries. If you compare South Africa to Ghana, for example, they have different composition mix, and these type of like factors may be correlated also with disease outcomes.
That's a very complex question you're asking there, and well-crafted. Very complex question there, and well-crafted. Now, what he's asking is a very, very important question. He's saying that imagine, let's drop seasonality for a minute, and we're comparing Ghana and South Africa. It could be that what impact we're seeing on inequalities in health might be because of racial disparities in South Africa. But that racial disparity is not found in Ghana, okay? So now we want to compare, just like I'm arguing now for seasonality, he's saying, he's putting it to me now that, now I want to compare South Africa with Ghana, and it could be that the outcome of the health may be because a particular racial group in that country is prone to that particular disease X, whatever. And because they have more of that racial group in that country, so the contribution to that disease burden is high in that country purely because of the presence of that race group in that country. Meanwhile, that race group is not in the other country. So now I'm comparing apples with oranges without trying to understand that the underlying cause of the other country is the race. I'm using the case of race, but it may not be, but something else. But race is the underlying cause in that country and not the underlying cause in Ghana. That's that. Yeah, technically the simple answer, it doesn't matter. But what he's saying raises a very important question, which I have to think.
I guess my point is that if it doesn't matter for racial mix, then why does it matter also for seasonality? Why should we try to make that correction?
No,
and that's the same point that I'm trying to.
I agree. No, but his point is a very important point he's making. He said, why should I worry about seasonality when I'm not worrying about that one? So that's his question is a very innocuous one. Correct.
Rather than race.
Correct. Now let me answer your question. Let me answer the question. I know. I get the point. Now let me just try and answer. Somebody wants to, let me answer the question. Now the issue is with inequalities. The first thing we need to do, the first step is to assess the differences between country X and Y in a certain outcome. The causes of the outcome are dealt with within the country. So now it's difficult because the primary, if it's a disease that is malaria, I like using or dengue fever, malaria, for example, malaria has a lot to do with season. The cause of malaria in itself is season. You cannot divorce season from malaria, okay? But it could also mean that you're dealing with a disease that is racial driven. Then in that case, you might make an argument for it. Yes. Hello. Now we've talked a lot about the theoretical things. Let's try and see if we can implement them. If you have your computers, you can pull them out. If you don't, then you follow me. You already have the materials. When you go home, you implement them. If you have Stata, and you can manipulate Stata. So I have series of codes here. So you don't need to do anything that much. The only thing you need to do is for you to change your working directory. For some reasons, my timing, this thing is very sluggish, but I hope it works. Okay, so the only thing you need to do for your do file to run is to deal with your working directory. Just tell Theta where your data will be placed, and that's all. The rest should be history. It should be fine. So in my own case, I have put my data in this particular folder. That folder, the path you see there. The path will be different from you. For you, so I cannot preempt your path. That I can't do. But I can put mine. So just change yours to whatever it is. Then we want to use this data I called malaria data. I talk a lot about malaria, okay? But not like I do malaria, but I talk a lot about malaria. So this is malaria data. Now the data you would see, we'll describe in a while. You'll see, before you even do that, I can show you quickly that this is what the data will look like. And I put there the source of the data. So you find variables like malaria incidence. For some reason, I use 2 time periods, so that if you want to do it, you have to go do yours and put the right time periods, okay? So it's also good for you to see illustratively how this works. So malaria incidence for about 50 odd African countries. So the data set we have here is an African data set. Likely because malaria is something that's endemic on the continent. And then the population is basically a population. Then the GDP per capita is a measure of income between countries. And then you have total malaria spending. Then we have the proportion of malaria spending that is from donors. And then there's something below, which I don't know, for some reason is cutting out, is total development assistance or spending on malaria. That is how much donors spend on malaria. So we have in each country how much is donors spending on malaria in each country, measured in millions of US dollars as well. So these are the kind of variables I have in the data set for now. So if you go back to that do file, that's that data set. I just basically showed you what the data set contains. This is the data set. So for some reason, I'm going to run just that so that we see what the data looks like. I will call that up. Good, that is it. For some reason, this is appearing. Let me make it a little bit good, this clearer. So now, if you take a look, you will see that the data set you have here corresponds to that which I gave you. Malaria incidence, population, blah, 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 blah. So we're going to use this illustratively to show many things. So what this first bit does is that I want to remove countries with missing values. Why is that so? Let me quickly show you. If I browse the data set, you will see that some countries, for example, Eritrea, there is no per capita income for Eritrea. For some reason, it's not reported. No per capita income for Eritrea. I don't know, for some reason. Then you also find Libya, for example. Libya doesn't have any malaria incidence report. It's not a zero. The countries with zero, you see, like Cabo Verde is zero, but Libya is missing. So I don't know what it is. And also, they don't have spending on malaria. It wasn't reported. They don't have how much to spend on malaria, equally missing. So we can't work with that data. Same with Lesotho, and some other countries. I think there are a few of them. There's Mauritius there. There's no malaria reported. No malaria spending. No, we don't know how much to spend on malaria. So you see, those are the ones we want to remove. Again, Seychelles, similar. Here, there's no per capita GDP for South Sudan, likely because it's a warring country. Again, no GDP. So what I want to do is I want a clean data set. This is the reason why I left this is that so that many people can see how we deal with many things in household surveys. This is a whole 54 African countries that we have, and some with missing values for some observations. And some of them, they are really, really missing that we don't know. Like Tunisia, maybe malaria is not something they battle with. Same with Seychelles and the rest. So what that command, which I will show you in a while, does is that this command is to allow me to just basically delete where there are missing values. So if I run these two commands together, it basically, it will tell me the number of observations that it dropped. In this case, I don't care what the output is. I'm not interested in the output. I want to use Stata's inbuilt ability to detect missing observations and missing values, and it dropped 7 observations. So if you go back to see your data set, you will now have data set that is complete. There are no missing observations. Can you see? So that's basically what it does. And here I'm not worried because I would say these values are missing at random because those countries may not, Tunisia, for example, may not be dealing with malaria. Seychelles, Mauritius, malaria is nowhere in the equation. So I'm not worried about it. That's another step. The one I would have worried about is South Sudan, but you cannot get a per capita income of South Sudan. Not possible. So that's pretty much that. So you now have your clean data set. Now, if you go back to our do file, next it generates what we call a fractional rank. A fractional rank is the rank that we use to compute the slope index that I talked about. So it's the work of Liman and Yishaki in their paper that appeared in Journal of Econometrics in 1989. So it's in that paper that they developed the fractional rank and used it for many inequality assessments. So if you run the command from here, don't worry about it. If you want to read in depth to know exactly what this command means, take your time, but that will give you the fractional rank. So if I run that, I will get the fractional rank. And the fractional rank will automatically appear in my variable window here. That's a fractional rank. So it will range from 0 to 1. So if I summarize that F rank, it's going to range from 0 to 1. But remember, I told you we want to deal with the boundaries. So you will not see exactly 0. You will not see exactly 1. That's the beauty of a fractional rank. Because if you have 0 and 1, if you're using it for some estimation, it will drop the 0 and it will drop the 1. And then 2 observations will just fall out because it doesn't want to see all zeros and doesn't want to see 1. So that's the beauty of the fractional rank. So you deal with those extreme values, gone. So it starts with a minimum of 0.05, 0.005 to 0.9999, which is pretty much 1, statistically speaking. So that is the same as ranking people from 0 to 1. So the richest person is the one with the 0.9999. The poorest person is the one with 0.0048, blah, 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 blah. Great. Yeah, I think people who are not interested in the practicals are not going to come here. So, but here, what this does here is that you will now basically generate some scalar. Scalar is what Stata will use to hold, pretty much hold a value. So if you tell Stata that it should, this QUI means quietly. You want it to quietly summarize this thing called fractional rank with the weighting applied as this, and then it should put in a scalar the variance of that. So it puts the variance of that in this, and then again you quietly summarize malaria incidence weighted, and then it puts that scalar here, the mean of the malaria incidence in 2021 we put into this scalar. So anytime I call this M_malaria, it knows what it means, that it's basically the mean of malaria incidence or average malaria incidence. So if I run that up to where I want it to drop, because I don't want, I hope it did it. I don't want it to keep, yeah, it did it already. I don't want you to keep those other variables. I don't need them anymore. Only thing I need is a fractional rank. And of course, the scalar that it already has. Now we are going to start our analysis proper. The first thing we need to do is the slope. I talked about the slope index of inequality and the relative index. Now the slope index is just basically the regression of malaria incidence, which is our main health variable, and the fractional rank, not the per capita income. So people think it's the per capita, not the per capita income. So you want to see the slope of malaria incidence and the fractional rank of income distribution. And that's it's just a simple regression analysis. So if you run that regression, it's a very simple regression analysis. And then what you need is that slope. So that thing you see here called B_B, that is how theta understands the slope of this fractional rank. So the slope of the fractional rank, I want to call it the SSI. So after running that, it tells us that the slope index of inequality is minus 217.1, blah, blah, blah. That is the slope index of inequality. So, you see, it's not bounded by anything. It's not zero. It's limitless because it depends on the mean value of the health variable. It's just limitless. So basically, that's the slope. The slope you see above here is the slope, is what it is pulling. Yeah, that slope is what is pulling and reporting there. That's the slope. So now the other one is but you could see from the slope that it's a negative relationship between malaria incidence and fractional rank, which means poorer countries have higher malaria incidence than richer countries. That's the negative slope there. Poorer countries have higher malaria incidence than richer, and that's how far you can say. That's magnitude means nothing. It's a slope index. However, when we move into the relative index, the relative index allows us to now basically normalize by the mean. If you remember, this M_malaria is a mean incidence. So you take that slope index and you normalize by the average malaria incidence. And if you run that, I'll run that quickly, and you will see now that it has been normalized, and the relative index is minus 1.24. Now, this is pretty much something you can compare with the concentration index you're going to see in a while. So the relative slope of relative index of inequality is what you see there. It's very easy to compute. You see, these things I was talking about it like it's something very difficult. It's very easy to compute. Now you have these codes. If you want to change the variables, you can put in what you want. You compute it's very easy. So don't get worried about the big names. Now, what I computed has no standard errors. So you could see this is the relative index. I can't tell whether it's significant or not. So I'm going to use another method that allows me to compute the standard error. So this command would do that for you. The command is not difficult to understand. I would try to explain. Oops, let me change the font slightly so that we can see everything. Maybe 16 should work. I hope so. Let's see. Yeah, 16 works. So at least you see everything appearing on the same line. If you remember, that index is still the same thing you see before, and you remember that as the same index. But now we have a test of significance so that we can tell that inequality is statistically significant. That's easy to do. That inequality is negative. Poorer countries have higher malaria incidence than richer African countries, using the data we have from the World Bank. Then next, we move to the concentration index that we talked about. The concentration index, to do that, you need to install a command written by O'Donnell and Co. It's called the con index. This is the command. It's called the con index. So if you need to be connected to the internet to do this. So if you run that code and you're connected to the internet, it will download it for you. You don't need to worry. Then the other code that you need to download is the Lorentz command. So if you are connected to the internet, you run this, it will run it for you. If you're not connected to the internet and you've downloaded it before, the command will still run because I put in something very important here. This thing here, this cap. This cap. This cap is a short form of capture. So it allows data to bypass when it's running the regression, running anything you're giving it to it, that if it runs into error, it will ignore the error and continue running. If you remove that cap, and you're not connected to the internet, the moment you try to run, you stop there, theta will just stop. But if it sees that it's unable to connect to the internet, it quickly sees that I've given it a cap. It ignores the error and it continues. That's the beauty of the cap. So the cap allows you to continue your regret, your estimation, whatever. You can put it in front of anything. So what you want to tell theta is that ignore any error and continue going like a zombie. That's exactly what I've told it. So I've done the same with the Lorentz, just in case you're not connected to the internet and you want to run this code and you run into trouble. So know that that's why that is the case. But for this class, I'm going to run it. I'm connected to the internet, so it will run. Okay, good. So I'm going to run just to that point, and then it gives me. See, it takes a while. It's running and installing. It's helping to install, and then it runs. And then it now tells me that my concentration index is that thing you see there called minus 0.21, whatever. Now that minus 0.21 is gotten from a method that uses the convenient, pretty much like a convenient regression method. Okay, that's pretty much like a convenient regression method. There's another way of running that using the con index. The results will be similar, but different, but similar. So that one, first of all, we need to SVY set. SVY set is we want to declare the survey settings of our data, how the data were collected in terms of the stratifying, the clustering, and the rest. But in this case, these are national data without any clustering or stratification. They are data that already exists from the World Bank. The only thing we need to adjust for is the differences in population between countries. So that's why the survey setting is pretty much simpler here. So if I run that with that survey setting, I get a different, can you see a different kind of index value, but similar. It was 0.21 something before, but it's very similar, just because they use slightly different methods for computing. But I would prefer to use this one than the first one, because this is pretty much the theoretical value if I run the model myself. So now what that estimate tells us, I will show you in a while, is that it's a significant estimate, which was similar to what we found with the slope index. Remember? The slope index was significant. I'll quickly go up for you to see. I hope I've not passed it. I think I passed it. The relative, yeah, I think it's this. Yeah, it's the same. This was the one that I now showed you, the one that can appear in the whole. You can still see that the p-value is about 0.0007 here, which is similar to what you saw at 0.006. Because they are very similar. The two indices are very, 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 very similar. Can you see? 0.007. Because remember I said you can get one from the other. So that p-value is pretty much the same, 0.007. It tells you a lot about similarities of the two indices. You can get one value from the other one. Okay. Yes, please. Yes.
To the detriment of the p-value.
Both. You should be worried about both. Let me, for those who are online, he's saying, should we worry about the magnitude of the index to the detriment, the p-value to the detriment of the value of the magnitude of the index? The answer is yes, we worry about both. But more importantly, the significance. Because the significance tells you that your results are not basically white noise. It just ran, if it's not significant, it means it's white noise. It's zero, it's just misbehaving. You don't even know where it belongs. It could be negative, it could be positive, but the fact that you see positive is just random. If you draw another sample, it might become negative. If you draw another sample, it just jumps. So it can't place it. So it just tells you zero. That's what the significance value, that's exactly what it means, because it cannot place where it is. So if it cannot place it, it's not significant. So it tries to find a place for it that it has more density, but it can't find it. So it's everywhere. So it says, no, I'm not significant. That's pretty much what it does. Yeah. If that helps. So no matter how large the value looks, yes. Correct. Now, what you're doing is, remember the incidence is already per whatever risk, population at risk. Okay. Now that is basically what you need. You cannot use the original number of malaria cases because the incidence already, because we want to compare Nigeria with Ghana with Gambia with, the best way to do is get the population, the incidence already adjusted by population at risk. The reason why we do this is that for the for you to compare two countries, in as much as you already know the incidence rate, the population in these two countries, they don't still have the same population. So you want to, because a country with the same incidence or with more people, you're not comparing with another country with the same incidence but with fewer people, it's different. Because you're going to compute an index as a summary of all the countries. So for you to compute a summary of all the countries, you must add the population to show that this is coming from 500 million people, as opposed to just this country is country A with X incidence, and then it treats each country as one data point without taking into account the fact that Nigeria, for example, has 210 million people. Ghana has, for example, about 40 million people or odd people. You know what I mean? That's, yeah. It's weighting, correct. Weighting. You already know the technical term, so I would have used it. Good. Yeah, now the constitution curve can be drawn using the same command, but you just tell it to put a graph at the end. So you see, it's the same command, but I just tell it, give me the graph, not just the index. So if I run this, sorry, I didn't. If I run that, it's going to give me the graph for some reason. Okay, good, it's coming. It takes. So that's the graph. I will show you a neater one. You can always edit this graph and remove whatever you want to remove. That gray thing you see there is just the 95% confidence interval. Oh my, I've told you to run everything. So it's basically, it's going to cause me a lot of trouble now. it's doing everything. So let me just stop it. For some reason, this computer can be a bit slow at some point. I hope I have not even closed my do file. Sorry, I have to reopen it. That one, I just need you. And I just need to open you here. You can go to sleep and you can come back. And then I get my do file back. Yes, please. Yes. Oops, sorry. No problem. I think you're talking of this link. Let me resume slideshow. This link? Okay. No problem. Are we good? Yes. Who has the mic? Where are the... Thanks. Thank you.
We took the rank variable, which is per capita GDP. In case of DHS, we would take the wealth index score or quintile, because I used quintile for my work. So
yes, you would use the wealth index score, not the quintiles. Yeah, if you use quintiles, then you have to do a weighted. Yeah, just use the quintiles. Don't even though it includes negatives, use the quintiles. Yes. Oh, no, sorry.
Factors.
The index factors, whatever you want to call it, the values, the scores. Yes, fine. Yes, the scores. Okay. Good. So let me start from where I was. I was there down to plotting the curve, correct. So I'm going to run back so that I get my bearing. Great. So it's going to come up with the concentration curve. That curve is, again, telling us that it lies above the line of equality, which means it is remember now, pro-poor, correct, pro-poor. Now that pro-poor nature, again, corresponds to the value of the concentration index, which we saw. It was negative. So they all speak to each other, negative. Then, before we move into this behavior, I will go quickly so that we can see how to interpret. It's also good to see how to interpret, not just showing the results and not interpreting. So the slope index we saw, I just copied and pasted. So it's the same thing, just to show you how to run it and how to interpret. But the slope index we saw, it was negative 217. That's what it was. So the meaning is that this is the difference, decrease in this case, from the richest to the poorest country, African country, in the average malaria incidence between, of course, the richest and the poorest country. So the absolute difference in malaria incidence between the richest and the poorest African country is 217.13 per 1,000 something people at risk, I think. This is negative because the country with the highest GDP per capita has lower malaria incidence than the country with the lowest GDP per capita. So that's the gradients. And that's pretty much what you see there. Now, if you go to the relative index, which we've just seen, if you recall, it was minus 1.241, blah, 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 blah. The same, that's pretty much copy and paste. The relative index is that. This means that it's a proportionate in terms of relative decrease in malaria incidence between the country with the highest and lowest per capita GDP. So it's a relative difference. Now, why is that so? Remember that the fractional rank moves from 0 to 1. Fractional rank moves from 0 to 1. So 1 unit increase in the fractional rank is moving from the poorest to the richest, simple. So that 1 unit move is moving from the poorest to the richest. And that's why we kept talking about the poorest and the richest, because the fractional rank, remember, is 0 to 1. So 1 unit move is moving from the poorest to the richest. So that 1 unit move corresponds to a change in incidence that is about 1.241. So that's why it's a slope. And the slope, of course, you can pick any 2 points, the slope remains the same on the straight line. Yeah. Now the concentration curve and the index. Remember the index was estimated at minus 0.206. That's what we have there. And that's the curve. I just removed the 95% confidence interval so that you can see the curve nicely. The curve, the index of 0.206 means that it is a pro-poor index. That means malaria is concentrated amongst poorer countries, unfortunately, or lower in richer countries. On average, the variable of interest, malaria, is higher among countries with lower GDP per capita compared to those with higher GDP per capita. Okay, now let's move on to our practical so that we do step by step. When we finish, we go back to interpret our results one after the other. Remember I told you about the behavior of the concentration index that I said, let us try and run practically with real life data that we see what's going to happen. So I'm going to again use the same data set, the same survey setting, nothing different. Then I'm going to do a little bit of some simulation, but real simulation, not a bad one, right, in that sense. So what this does is that I'm creating a data set that has nothing, just observation. Is only one observation. There's a variable called number, I call it missing. CI simulated is missing. I want to also get what the work staff index would be, the areas index, and then I save the data in this file. That's going to be a file. So let me just run this from here to here, and then you would see it just does that. It saves, sorry, it's going to save my data for me. It has saved it somewhere, okay? And it's going to save it in your working directory anyway, so you don't need to worry. In my case, it has done it for me. Now, what I want to now do is I want to populate it. To populate it, I said, let me generate a variable called malaria is equal. Let me create dummy, because our worry is that we're dealing with dummy variables when we do the wax up and arrogance. So let's just create a variable called malaria is equal to 1 if a country has any malaria incidents. We don't want to know what it is, but there is malaria incidents in that country. And replace it to be 0 if there is no malaria incidents. So the whole idea here is we want to see whether if poor countries, if we start eliminating malaria from the poorest country to the richest country, what happens to that index? Let's imagine Africa comes together to say, now let us begin to eliminate malaria. What happens to the index? Can we use that index to now compare countries? That's exactly what I wanted to simulate here. So I will run here. So it's a hell lot of code for me to explain, but I'll try and explain. I'll try as much as possible to explain the one I've just selected. Let me see. I'll try. So when you see quietly, I think I mentioned earlier, when you see quietly, it means that you want to run the estimation without seeing the output quietly. Stata will do it quietly, but it will do it. So the first one sorts the countries by GDP per capita from the poorest to the richest. And then I counted. Counted means I just wanted to know, it's actually innocuous. I just wanted to know the number of countries I have there. Then I'm creating a local. A local is like, it's called a macro. So I want to hold in that macro called max n minus underscore n minus 1, which means if there are 47 countries, I want to hold 40. I want max to be 46. Just remove 1 from the total number of countries, and you'll see why that is the case in a while. So I'm now saying for values of I, whatever I is, that will begin at 1, incrementally at 1 to that max that I've created, which will be the 46th country or whatever. I want to be doing it 1 by 1. So it first starts with the first, the second, the third, the fourth, the fifth, the sixth, the seventh, down to the last. So I want to keep replacing it with eliminate malaria from the poorest, next, keep replacing it with 0, 0, 0, 0, 0 until, and every time it replaces it, it should compute a concentration index for me for all of them. If anytime it replaces, when it replaces, you remember, once it replaces, the old one has already been replaced. So it's cumulative. It keeps replacing until it gets to the last one. The reason why I didn't include the last one is the concentration index is not defined when all the values are 0. If all the values become 0, there is no concentration index because it's 0, nothing. So that's why I eliminate the last one. Will keep its value, just because if I give it a 0, it won't run. The concentration index is not valid. So that's the reason why I did that. It's just for estimation sake. So every time it does that, it keeps doing that, and it does that, and it saves that data for me in the one I created. So we will now have a data set that gives us that information. That's what this does. So I will quickly run this. You see, it does up until whatever you see here. Then it plots, then it's going to plot, it takes its time, it's working. The hell of commands there. Good. I think I will have to run them 1 by 1. They're pretty much the same graphs, but presented differently. So to make it easier for us to see them one after the other, let me run them one after the other. Yeah, let's do this. Let me run this, and then let's see what that tells us. Perfect. I think it has run it. I hope so. Then the next is this. Sorry. Just that. I think it did run. I shouldn't even worry about it. It's run that before. I will use this, merge that. Aha, okay. I just need the first graph, which is the two-way graph, the first one, this one. So now what this does is that, oops, this is another graph, sorry. This is another graph, sorry. I have jumped, oh my goodness, I've jumped to another section. So sorry. Oh no. Then I have to rerun this so that I don't get into problems. Sorry, let me run from here. Okay, yeah, just do this. That's it. Okay, Now I've just done the first one I'm plotting is a basic plot. I think I use a line graph here. It's gonna come. It's gonna come. Takes a while. It's gonna come. Takes a while. Yeah. Now you will see. This just uses a line. It's going to be the same as what I'm going to show you. You will realize that when the bottom X countries have no malaria case, this is, let's say the bottom 10 countries have no malaria case, you can see the behavior of the 3 indices. This is the original, the standard CI. This is the Eregas corrected CI, and this is the Wagstaff CI. You would see that somehow, at some point, they behave alike. At some point, they are divergent, very, very divergent, extremely divergent. And you could find a case where you would pick this point here is low and it's high there. And then again, it's low here. So are you now saying that you could see that mirror playing out, that you would say this inequality here is the same as that inequality, or this one is the same as that inequality. But you will never see that with the original CI, because there cannot be any 2 distributions like that with the same CI. So that you can compare them. But the Eregas one, there will be 2 distributions with the same CI value, the same. Because of that cap, you will find that. And the Wagstaff one behaves pretty well, tracks the CI pretty well, but not the Eregas correction, which is the kind of problem I'm talking about. Now, this is real life. So let's imagine the African countries come together to eliminate malaria. That would be the problem they face if they use the Eregas one, for example. So you don't know which is playing out, which is very, very problematic. So the other graphs are pretty much the same. It's just showing dots as opposed to a line graph. So it's the same, just dots. Then you also have this is a clean plot. I'm going to show you a cleaner plot. So the clean plot is just making it real look better. You can also have the same clean plot for the dots. Pretty much the same. Lots of code there, don't worry, but it's a cleaner one that tells you how these things behave. So you could see the dots could be similar for the Eregas corrected one, but you can never have the same. In that. Great. So the next is what we talked about in terms of socioeconomic inequalities, in socioeconomic health inequities. Remember the need versus the use. So you don't just look at use of health services, but also compare that with need. So in this case, we know that malaria spending should follow malaria incidence on the African continent in terms of donors. When donors fund malaria on the continent, their funding should follow malaria incidence. If their funding does not follow malaria incidence, then there's a problem. That's inequitable distribution of donor funding for malaria on the continent. So that's what we want to find out. Are donors funding in such a way that it's equitable or not? We'll figure that out here now. So we use the same data set, we survey set it. The tab stat is basically a way to show us, the tab stat is just a basic way of showing us the values. Before I go there, I think I need to also do the interpretation, which I didn't do for the behavior of the index, but I talked about it. This is basically the intervention, the way it behaves. I use a simulated example. The meaning is that the choice of normalization scheme matters significantly considering the 47 countries included here. At some point, you see the Eregas and Wagstaff's normalization being similar. At some point, you could see the red and the green similar at some point, but at some point they diverge. So again, but the standard index kept its pace, behaving as you expect, because as you move from the bottom to the richest, you expect that as you're eliminating malaria, you pretty much, the index should become pro-rich as you move along, and it's behaving as expected. But the rest are not behaving as expected. At some point, it's becoming even pro-poor. After you've eliminated malaria among the poor and you're left with the very, very rich, the Ehrlich's index is not tracking it well at all. It's becoming even more pro-poor, which shouldn't be the case there. And that's the major area of worry. The same here, the same thing, just the different graphs. So now this is the one I'm going to show you now in terms of health equity. So now that we've run that, that's not necessary for us to see. We're going to generate per capita malaria spending. So now remember, we're dealing with malaria spending. We need to also know per capita within a country rather than just taking malaria spending the same way we did with incidence. You don't just use malaria spending. So we need to know per capita, per population. Although the ideal thing to use here, which I don't have, is per population at risk. Okay, that's the ideal thing to use. But I didn't have the exact number of people at risk of malaria in my data sets. And so I use a proxy here. So I generated that per capita, and then I used this code you see here. This code is a little bit complex, but it does something for us. I'll try and explain. It ends here and restores. So the Lorentz allows me to generate that EB, which I'm transposing. That thing you see there is transposed. I'm transposing that so that it becomes a column. And when it becomes a column, I want to send it into a data set. I want to get it and quickly put it in a data set called incidence. So that's why you see the SV mat, save matrix into the Stata data set. So that's what the SV mat does. That thing you see above there does the magic, collects it for you and puts it in that data set for you. The preserve and restore is, I don't want it to distort everything I've been doing before. You should just do this. It's like a thief coming into your house and going out without leaving a trace. That's what that does. It comes in, does the analysis, goes out without leaving a trace, but it has done what it has done the harm, whatever it wants to do. But it goes out without leaving a trace. So that's what the preserve and restore does. It allows you to penetrate it, do whatever I want to do, go out, leave no trace. So when you do that, it saves the data it saves that data in that file called that. And when you go back, you see it doesn't touch your data set. Your data set, the original data set remains what it was. It just came here, you gave it room to do whatever you want to do, save your own data set and go away. But I keep me where I was. So it's basically what that does. It's used a lot in programming. So if you do a lot of programming in Stata, I won't be teaching you that. Okay, now we do again the same here. We've done for malaria incidence. So we now have here the coordinates we use for plotting the concentration curve for malaria incidence, which is the measure of need. Now, malaria spending is basically how much was spent on malaria. Does that follow the need that we've identified here? So we'll do the same, very similar commands, if you see. The only difference is now that I'm working on malaria spending and I'm putting in a file called spending. The same thing, it comes into Stata, does the work, keeps my original data untouched, but it has done the work for me, which is very good. Okay, now I now need to merge those two data sets that it has created. It did create those data sets, even though you don't see them, it's already created. So I want to merge them. Then after merging them, I will plot the concentration curves myself. So it's going to do that for me. Let me quickly select that and run that. So it's done that for me. So you would see quickly that the incidence of malaria is the incidence 1, and then the red one is the spending. Somehow it tracks it well on the continent, which is a very important finding for us. It's a very, very important finding because it shows that donor funding, though they are not coordinated across countries, but they are achieving equity in a way. You see, it tracks it well that donor funding for malaria follows need on the continent, which is a very, very important finding. And for policy, that we could also use the same kind of model for other diseases, HIV, malaria, HIV, TB, etc. So now let us do the index. So now we've compared the curves. So let's compute the constitution index for both and find a difference in the constitution index, whether it gives us the same thing as what we've seen with the curve. And that's exactly what this command is going to do. We call up the same data. We generate what we generated before. Then we're using the concentration index. So we're computing the indices ourselves. So the index for malaria incidence, the index for spending. So you see the two indices. One is 0.2, minus 0.205. We've seen that before. Then the other one is minus 0.216. We can't tell whether the difference is going to be significant or not, but looking at them, we know it's very close. But we now need to apply statistics to this to know whether one is bigger than the other or smaller than the other. So to do that, we can bootstrap. Who knows what bootstrap is? Who's ever heard about bootstrapping? I hope I'm not losing everybody. Huh? Am I going too technical? Or you want us to do a little bit of some exercise? Who knows what bootstrapping is? Yeah, okay. Bootstrapping is one of the ways. There are many ways of generating standard errors if you don't have what we call the analytical standard errors. So you just sample a data, get the variable, get the estimate you want, resample the data with the same sample size, get the estimate you want, and keep doing that up until the number of times you want it to do it. And then you use that distribution to generate standard errors. So that's what we're going to do. But we're going to use Theta's inbuilt commands. Theta allows you to use its own command. You can decide to do it yourself. You can use Theta. Sometimes I do both. But let me use Theta as one because it's well optimized. So I'm going to write a program. So I'm going to write a simple program. It's a very simple program. This program, you'll see in a while, is done. That's the end of the program. That's a complete Theta program. It looks short, but it's a full program. So we first of all checks whether there's a program called diff_CI. If it is there, you should please drop it. Okay. Remember the cap. If it's not there, don't worry. Continue. Then the program is now defining a program called diff_CI. This is the same way every Theta program you know is entered. Like you have regress, you have mean, you have every, it's written the same way. This is how it is written. There's no magic. So you only need to define it. Now, if you define it, Theta knows there's a program called diff_CI. If you put in that, it will ask you, please give me more information. And how you want the information to be entered, you need to tell it. In this case, I didn't bother because I'm doing a simple thing. So I didn't bother. So in this program, it will compute the constitution index for malaria spending and then put it in a local called CI_spending, and then also compute the constitution index for malaria incidence and put it in the CI_malaria. And then there's a return scalar there, you see, return a scalar called D_CI, which is equal to the difference between the CI of the spending and the CI of malaria, so that I can use that in bootstrapping. So that is what that does. So now Theta is aware, my own Theta is now aware that there's a command called diff_CI. So if I enter that command, it knows what to do. It will just do it for me. And that's exactly what I want it to do. And to do that, I use that command called, this is the command you see here, but I want it to bootstrap equity indicator for me, which is that difference in the CI between the two of them. I want 500 replications. Maybe in the interest of time, I will do 50. The same, it just does more replications. But if you want to get a better result, please use up to 500 replications. So you see, can you see that bootstrapping? It's started, is run the command, is bootstrapping. It just does that for 50 for me. It's okay. I didn't tell it to do more than 50. This is the difference that we could have computed with a calculator. If you had time, you'd have computed it. You get the same. That's the, and then now you could see the standard errors. In this case, I used 50 replications, so it will not be the same as what I'm going to show if I go back here. It will not be the same. You've seen this already, that there's no conspicuous difference. Great. Oh my goodness, it's hidden below. But I'll try and show it. Don't worry. I will find a way around this to show this. Yeah. So that's the equity, what you just seen. But here I use 500 replications. As opposed to the one I showed that I used 50 replications. But the difference is the same. You see, it's not minus 0.0105, which is basically if you subtract this from this. that difference, that's exactly what it is. So the bootstrapping allows me now to compute the standard errors after taking a difference, which will be difficult to do. You only use a calculator, but you will not get the standard errors. But this bootstrapping allows you to get to that. Okay, we're almost there. The other part is the decomposition of the concentration index. I think this should be the last bit. This is the last bit. So we're almost there. It's the decomposition of the concentration index. We talked a lot about the social determinants of health. If you want to read more about this, there's a paper here. It's quite an old paper, 2016 or thereabouts. It's a paper on Nigeria. So the data I'm going to give you is slightly modified data from Nigeria. It's modified because I didn't obtain permission to present the data as it is. So I just, once you modify it, it's no longer the same. So the data is modified, but the results are similar to what you see in the paper, but it's a modified data. So it's not pretty much, it's not the same as the one in the paper, but very similar. So if you get the one in the paper, you run it, you get the results, basically. Okay, so I'm going to use that data called immunize. You have it already. I gave you the link. There's a variable called prop vaccination, which is the proportion of vaccinations that children between the ages of 12 months and 59 months have received. I'm going to bound that by that because I expect that full immunization only kicks in at age 12 months. I cannot assess full immunization pre-12 months. So between 12 months and 59 months, people should have received the DPT3, what's the vaccine again? It's DPT3, correct? For full vaccination. I think we have doctors here. I should be asking them. I think DPT3. So now what this does, the first three commands, apart from the use, is to rename that variable called Y, just want a Y, and then rename log of per capita expenditure, call it X. Nigeria has 6 geopolitical zones. So I want to call that dummies. Just call it dummies. So that's what those commands will do. If we go back to Stata, it's run it for us already. We don't need to check, but if you want to check, we can do that. Now we create a global called X. The global X is basically putting into X a selection of variables. I just picked about 5 variables, 5 or 6 variables there, 6 of them. One is the age, the other one is age squared, one is male, and then one is rural, one is whether the mother is literate, and X is the per capita log of per capita expenditure. So I want to drop this in this data set, children that are less than 12 months and older than 59 months. I just want children between the ages of 12 months and 59 months. Okay, that's what those commands I've selected will do. Then again, I want to do this regression to drop observations that are missing. I want a clean data set where there are no missing observations. Let me see how many observations I dropped. Nothing. So it's okay. It's clean. Nothing dropped. So I'm not even worried about it. Then I'm beginning my analysis. Now, this analysis is pretty much similar to what we've seen before. So I'm survey setting, basically. Usually you survey set. And then we do the concentration index that I want to decompose. That's it. So I show you what the concentration index will look like. So in this case, we have about 19,000 kids aged 12 to 59. It's a very large data set. The index is telling us is about 0.148. That's what the concentration index is, which is pro-rich, which means richer children tend to have more immunization than poorer, more vaccines than poorer kids, unfortunately, in Nigeria. That's what we found. So now let's see how we can decompose that using the WAG-STARS approach. So I'm going to write again a simple program. So this simple program would decompose and generate the standard errors for you at once. So you can adapt this in your publication. It's easy. There's no copyright issue here. You can copy it. It's one of the advantages of attending this class. So you're lucky. So you find out that in many applications, people don't generate a concentration index because they don't have the either capabilities to bootstrap to generate the SE, the standard errors. So I will not attempt to begin to explain this in detail, but what this does is that, remember the process. You first of all find out whether there's any program called decomposition. You should please drop it. If not, continue and then define the program. An R class program that allows you to do many classes. R class is a special kind of class that allows you to return results in a special way. And there's E class, which allows you to hold matrices. But I'm not interested in matrices. I'm just interested in scalar. R class will do it for me. So I want you to hold my result in R class. That's what that R class does. It's like having a different class. Then it goes through the process of estimating whatever I want to estimate, the constitutional index, the elasticity, the contribution, which is the product. Remember, the product of the constitutional index and the elasticity gives you that, where I put that big summation. Then I needed to add the unexplained terms, etc. So that's what this program does. It's a complete program. So if you run that up until where you see end. Once you see end, you know the program has ended. So this basically puts the results in some nice scalar for me, which I can call up if I'm interested, and end. That program ends. So I want Stata to quickly run. I've given this program to Stata. So in Stata now, it knows that there's a program called Decomposition. So if I put Decomposition, it will run it for me. To run it. So I can say decomposition because that's how I called it. It takes its time. It's still running. If it finishes, it gives you a dot. It's finished. I didn't tell it to display any result. I could have programmed it to display result, like any other result, it will display the result. But now I just want the result to be held in memory so that I can use the result. And how do I use the result? I use the result by bootstrapping. You see, this is the command here, but I want it to report the constitutional indices, the elasticity for me. But to do that, I need to set what we call seeding. Who knows what seed is? Who knows what seed is in Stata? a lot of new things. Good. It's not just in Stata. Yes. Yes, it's just like a circle. You know, when we talk about random numbers, there's no such thing as random number, but there is pseudo-random, okay? Random numbers are generated like randomly. I can say this is one. I pick something from a basket. I pick a number randomly. But computers have to generate random numbers. And there is an order to which random numbers are generated. So what that seed is telling it is that the order that it will generate random numbers will remain the same. Then you begin to think, is it really random? It's pseudo-random. So in computers, random numbers are really pseudo-random numbers, except you do some combinations. So this order means that if you run this command, you get the same result as any other person. So long as you tell Stata the order you want. And that's why I put the 1654. I can change it to 3897, whatever. So all of us will get the same result. But if I remove that seed, we all get different results, but similar. Because the order in which it draws the sample would vary. So that's the whole idea behind seed. You seed it. You give it a random number seed. Then the replications is the number of times I want it to give me my to draw the sample. It keeps drawing only 50 times. I can make it 500 or whatever. We'll be here till the plenary is over. So that's the challenge with that. So now let's quickly run this. I think we're good with time. We can even finish up before time. So I'm going to see that at that and just run just for the constitutional index alone so that you can see how that works first before we go further. It does the same thing with the equity one we saw. It's going to take a while, but not really that much. So it runs every time it picks, it draws the sample and it estimates it, it puts a dot. I can tell it to show no dots, okay? But it's good to see the dots. And it keeps doing this until it finishes. When it finishes, it will give me a table that would show us the constitutional index, the bootstrap standard errors, the confidence interval, and the p-values, whatever. But here, originally, we had the constitutional index estimated with its analytic standard errors. If you want, you can go back and compare. You'll see they are very similar, very similar. So it's up to you whether you want to retain the analytic standard errors for the constitutional index, which you already have, or you want to go by the bootstrap. If you bootstrap using 5,000 replications, the differences will be 0.000 negligible. So you now realize that the two kind of converge because of the power of the normal distribution. It's the power of the normal distribution. So if you study statistics, they talk a lot about the law of large numbers. Law of large numbers is a powerful law. It shows you how many things converge once the sample size becomes really, really, really large. So while that is basically going on, I will show you the results.
John?
Yes.
Just sorry, I'm trying to do live as well.
Oh,
and for the bootstrap, in fact, after running your program, I couldn't find the difference, but it says that the option rep is not allowed. Is it a matter of like Stata 16 and 17?
No. I'm glad you raised that up. So we'll deal with it. Now, the reason why it tells you that is rep. I put rep in as a local. And when you put that as a local, as opposed to scalar, and I didn't want to use the scalar for some reason. Local is very weak. It's not strong in Stata. It just, the moment you run a command, it just loses itself. It's gone. That's a local. But a global is so strong that after your Stata session, it's still alive. But local has short lifespan, it dies. So the only way to keep a local is you must run the command with the local. If you run the local separately before you now start running the command that calls that local, it's gone. It's long dead. Yeah, it's long dead. But if I had called it a global, it's still alive. You can call it up. So a local dies easily. So you have to follow through and run all through. If you get what I'm trying to explain? Yeah, so select that where it starts by saying local reps equal to 50 or whatever, yeah, and then run through. You'll be fine. You'll be fine. So now this, no, not this. Yeah, that's great. When it finishes, I hope it has done that. For the constituent index, you're going to get that. It gives you the coefficients of the index, the bootstrap, the Z value, the P value, and the confidence interval. And it also gives you the same for elasticity, same bootstrapping for elasticity. And it also gives you for the concentration. It's going to give you the three tables. So you pick the concentration. In this case, you see the contribution of residual is very, very minimal. If you add all these contributions together, you get the 0.1476, whatever that is. You'll get that. If you want to take your time to add them up, you will get that. And then the beauty of this is that now you have standard errors that you can check which is significant and which is not significant in this case. Like, for example, the literacy of the mother determines whether the child is immunized. It's a very important factor here, the literacy of the mother. So mothers that are literate are more likely to send their kids in for vaccination. And then those that are not that literate, rather than saying illiterate. Then also income plays a very important part there. The X plays a very important part. And the regional dummies in the context of Nigeria is very relevant because vaccination rates are not the same between the North and the South. So wherever you live, it matters a lot in the context of Nigeria in terms of access to vaccination. So people in the North tend to have very low vaccination rate compared to people in the South. So regional dummies are coming out as very, very important factors to look at in terms of what drives disparities in vaccination. So these are the things that policymakers would want to know. Now I know there is inequality in vaccination rates. How do I act? The policymaker needs to know that target literacy of mothers, because once mothers are literate, they will be able to vaccinate their kids. Also, where people live matters. Whether they live in rural, urban matters. You could see it's significant at least at 1%. It's pretty much on the dot at 1%. So whether they live in rural or urban is important, as well as the regional dummies, whether they're in the north of Nigeria, the middle of Nigeria, the south of Nigeria. It's really, really important. The residual is negligible here. That means it's okay. If someone asks about the magnitude, whether it matters, the fact that it's not significant, I'm not worried about it. I don't even want to interpret it because it's noise. A p-value of 0.4 is really, really high. It's a very high p-value to interpret, to give meaning to it. It doesn't matter whether the child is a boy or a girl. Vaccination rates are pretty much okay, which is good. We like that. So there is no preference for boy or girl in the context of Nigeria. There may be differences if we do disaggregation by region. Maybe the north, you get something different from the south. But in this case, I didn't. But if you want to, you have access to the data, you can try rural, urban, north. We have all the regional domains. So you might want to say, let's do for the north, compare with the south. You find different results. Yeah. Age doesn't matter that much because they're pretty much in the same age range, 12 months to 59, which is okay. Then we now know that there's no preference for older kids and younger kids or something of that nature. So that's pretty much what we found here in that paper. So you can read up the paper if you want to. Yeah, so this is the first part, which is similar. I won't run the rest. It takes a while, but once you see that the results are corresponding to what I've just shown you, you see that the first one is minus 0.004 something there. Yes, please. Okay, good. Oh, good. You're talking to economists. Who is an economist here who can bail me out? Aha, good. Let me stop talking. We speak the same language, so he will bail me out.
Well, let me answer why we have h and h square.
Yeah.
Well, when we add, it's the first one of it because it's not a normal variable, and we add square. I'm doing it purposely, every time without asking myself the question, actually.
I have thought because, for example, because of something like the utilization, the use is going up and down, and when you control for square, h square is going down. I'm not sure yet, but something like that.
Yeah, pretty getting it. Somebody else wants to try? You want to try? Okay. Oh, yeah.
Yeah, I think the age there, we are looking at the age at which you are, but for the age squared, as you increase your age, how does it change the inequality itself? So the age squared is trying to capture the longer term in terms of the time. As you get a bit older, how is the inequality changing? Yep.
Yeah, so I pretty much agree with him. So the age has to do with the current age of the individual. And then what happens if the person's age advances or the person's, age increases? Then what's actually happens?
I'm Jean-Claude from Burundi. So when we include the age square, it adds more information about, we are actually constraining the estimation to be in a quadratic form. And for instance, when we see a negative coefficient there, it tells that there is a maximum age. There is the concavity it's bent. I don't know if I'm doing it. There is a maximum, and then we then will be inferring for younger age and also for later age, and then we know that from younger age to the maximum will be increasing, and then will be going down after the maximum of the age.
I guess it's something like what we know about standard deviation and variance. So is it like, I think so that maybe A is seems to standard deviation and h squared is displaying like that variance. We know that we require the both statistics for for defining a distribution properly. So I think for that purpose, it's this.
I just have a question. Why did you stop there? I still have a h and h squared and h cubed. Another way to control for h is the h group. You make the h group, and then you can see the sign of the coefficient. Yeah.
Yeah. Good. Now let me talk about. That's why I say let's economists come in. People who are non-economists, there are many ways to get around it. Is they use age groups. If you don't use age groups, why economists do this? It's been captured somehow by what people say. Is a non-linearity of relationships. Okay, let me give a very simple one we do with health service utilization. We know that health service utilization is such that at a very young age, utilization is high. As you get older, it drops. As you get to mid-age, whatever you define as mid-age, it drops. And then as you get older to old age, it goes that way. So if health economists want to model or want to run a regression and they're including age and the variable they're interested in is utilization of health services, they cannot keep only age there without the h squared, because h squared is now able to capture that non-linearity in utilization in relation to age. So the coefficient, he brought in the coefficient. In that case, the coefficient will tell us the nature of curvature, whether it's a U or an N. Whether if it's negative, we know that definitely it's going to be an N, and if it's positive, it will be a U. So usually when we do utilization and we see if you give me an estimation and I see a negative in front of the utilization, I'll query you, I ask you, there's a problem wrong with your estimation, because I don't expect utilization to be the highest at the young age of 18, 17, 19. I would expect that utilization is such that it follows a U, such that I will see a positive in coefficient for h squared. Another way of going around it is what you said, you group them, and then you know which one is bigger than the other, okay? But that will give us more variables in the equation. Economists have what we call micronumerosity, in the sense that it's general, even in statistics. With micronumerosity, you're trying to estimate a certain number of variables, a certain number of statistics from a few data points. So you want to reduce your number of variables so that you don't run into micronumerosity, for example.
And like curve, that means adding both variable age and age square, you are adjusting the U and N like curve to adjusted estimate.
Correct. You cannot put in the square without the base, the level. Yes, you have to put both. Yes, you can't put the square without putting the level. The one without is usually economists call it level variable. You put in the level variable, you cannot just leave the level and put the square. You have to put the level and the square in together. They have to, but the square would allow you to check the non-linearity and you figure out if it is significant. It's possible that you find a non-linearity and it's not significant. It means I can as well run the model without that, because the non-linearity is irrelevant, and just keep the level. You can drop that. But in this case, you see, depends on what you run. Some significant, not some. So it has to pretty much go in. I can't drop it because of one and not the other. Yeah, it has to go in for both, for all, for the elasticity, for the concentration index, as well as the contribution. Yes.
I understand what you have explained, and thank you for that. I just have one question relating to the model. The SEC values are so high, and I just wonder.
The what? SEC value?
The theta, the SEC.
SEC.
Oh,
the Z. Okay,
the Z.
Sorry. Yeah, sorry. I just wanted to
sure the SEC values are quite high.
Yeah.
In this kind of computation, do you mind that they are so high? Because for me, it just something informed that it's endogenous variable, something like that.
Very interesting. Now, keep in mind, this is not a regression. Okay, I think that's where many people are getting. This thing you are seeing here is not a regression. This is not a regression. So what is, I will explain why it's high. You agree with me. This is the constitutional index of age. This is the constitutional index of age squared, constitutional index of male, rural, modest literacy, and X. This is the constitutional index of income itself. So that's the reason why it's the highest, because it's itself. So you don't expect that relationship not to be that high. The relationship is not that high, it doesn't give me that high, then I know there's a problem, because these constitutional indices are generated using X itself. So its own constitutional index should have a very high Z value. That must be the case. If it is not, if I see a paper and that doesn't happen, I'll ask you why. There's something wrong somewhere. If it's not even significantly worse, I mean, there's something wrong somewhere. Again, you realize here, urban areas tend to have very high, in terms of wealthier, okay? On average, tend to be, you find more wealth in urban areas because you're using income. You find more wealth in the urban areas than the rural areas. And because here, if you notice, this is a rural area. That's why the index is negative, because more wealth in the urban area. So if I change this to urban, this will remain the same, but this will be possible. And this will be pretty much the same high, telling us that there's a very strong correlation between wealth and residence. And you agree with me. I mean, this is income. People who earn the biggest money in oil companies and whatever, they're in the urban areas in Nigeria, not the rural areas. For male, it's not surprising. It just tells us how random male-female is. It confirms it. So households don't discriminate. I say, no, this is a girl child. I'm not giving money. I'm giving money to, yeah. Just tells us how random that process is, and it's a good confirmation. Modest literacy is again related to rural urban. Literate mothers tend to be in richer households. It's obvious. Literate mothers tend to be in richer households. So that correlation is positive and heavily significant, and I expect that. So the fact that it's very significant is an expectation that is really, really is high. It's high expectation, and it's met. Yeah, it's met. So this one is pretty much, I wouldn't worry about this that much, because these ones you can easily explain. Elasticity is hard to explain, but remember, this is the rate of change in the dependent variable, which is health. In this case, is immunization to changes in age. It's a very hard one to explain. Don't ask me to start now, because it's going to be a hard one. I can try, but it's going to be a hard one. So it's the responsiveness of age to changes, responsiveness of immunization coverage to changes in age, changes in sex. But in this sex one is a dummy from 1 to 0. This is again 1 to 0. This is also mother is literate, mother is not literate. The beauty of the literacy here is that we use not just English, okay? Because Africa is not just English. Whether you can read, it could be Hausa, it could be Yoruba. So long as you can read something, you can read. It doesn't need to be English to be able to read. Any local language that you can read, you can read. It's about literacy, not English literacy, but literacy, basically. And Nigeria, you have in the north, for example, where Hausa is well used, and it wants people to read that they can write, they can communicate. And people are taught in the languages as well. Yes, please.
It's not a regression. That's what I understood. So Z doesn't mean what we think on the regression. Or
yes,
the slide.
regression. Yeah.
So the same, we shouldn't care about the p-value or the confidence interval neither, or
no, we should. We should, because they are estimates.
Because
because they are estimates.
I'm a bit confused.
Sorry, sorry. Let me take a contribution. Let me stick to the contribution. So it just appears in the regression format kind of table, because I'm using the bootstrap status inbuilt bootstrap command. So this is how it appears. I can reprogram it to appear anyhow. But why do I have to go through the pains? It's a very useless thing to do in my life. To begin to do that. So what this does is that it just gives you the variable that we have selected. It tells you to observe the coefficient of the variable, whatever it is. So in this case, it's the contribution of dummies to the constitutional index. This is it. And it tells us the standard error of the contribution of dummies to standard to the CI. It gives us the Z value, the P value, and the normalized. I can change that if I don't like using a normalized confidence interval. But basically what this gives us is that it tells us whether this is a significant value or not. This contribution, whether it is significant or not. It's very important. Yeah, the residual is not significant, so I'm happy. It means my model, technically speaking, is well specified. This again is not significant, which is okay. Male means households don't discriminate boy or girl who gets immunized, which is, if that were to be significant, it's a serious issue that Nigeria has to deal with. If it's male that's preferred over females, then there's a problem. Because if there's any outbreak in the household, it doesn't respect sex. The outbreak is going to kill. If you immunize one, you immunize the other gets it, then you're not helping yourself. You're shooting yourself in the foot. Yeah, so that's pretty much it. Yes.
So are you saying that if you sum up the coefficient, you'll get the concentration index?
Yeah.
So this is just the individual contributions from the various variables in there.
Right.
All right.
That's why. And that's the last slide I wanted to show you how I did it myself. I wish I could just repose both so that you see them. This is like a copy, and to make it easier, rather than having many of them in. So, and again, not to make it very dense, I removed the S standard errors and p-values, but you have them if you want to use them. So if you sum up the contributions, you can quickly take a look. The age one is minus 0.00108. If you go back, is 0.00108. Blah, 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 blah. The last one here is the residual, is 0.032. It's the same, just the same. I just basically copied it. The residual, 0.032, blah, blah. So if you add that together, you get, because of rounding up, okay, it's the same. You round up, you get 0.147 something, but it works up to 148. Then the percentage contribution is saying that what is the contribution of literacy of mothers to the concentration index? So it's basically this divided by this in percentage. What is the geographic location? Remember the zones contributes about a third of variations in immunization coverage in Nigeria is contributed to by regional disparities. Regional disparities account for a third of immunization inequalities in Nigeria, compared to the largest, of course, is per capita expenditure. It's all about the money. Yeah, the other ones are negligible. I'm not worried about age, 0.7, 0.4, 0.00, 2 point. The unexplained is 2.2 is negligible, but again, it's all adds up to all add up to 100. Yeah, that's a positive index, which means the proportion of vaccinations received by children in richer households is higher than that received by poorer children coming from poorer backgrounds. Most SES-related inequalities explained by direct effects of per capita expenditure, by some things are cut down there, by literacy of mothers, and the geographic zone that people come from. Does that make sense? So that's pretty much how that will take you to the original paper with the real, this, like I told you, I didn't collect permission to give you the data. So once you alter the data, it's not the same. So I can as well simulate that data for you. So yeah, so that's pretty much it. You can look at it. It's a paper in Health Policy and Planning, 2016 or thereabout. So with that, I think I said that's the end. Thank you.
Thank you for the nice presentation. Though I joined in the middle, but I was in another session that was very attractive. But I notified that I have to attend this. So just a supplementary question that you show us the starter code. Is it also available in the download?
Let me know if you can access it. I'm happy to. Who also had access to it? Just raise your hand. Please.
Starter video.
I'll show you the code and the QR code.
Oh yeah, it's over there. Okay, thank you.
Yeah. So you just take a picture of it and download it. You have the computer, the SCADA code that allows you to do the decomposition, and you get the standard errors. You might want to tweak it here and there a little bit. Yeah. And also, if you want to compute the slope index, the relative index, everything I gave, it's there. And if you have any questions, any queries, you can always drop me an email. I hope if I have the time, I'll respond. I'll try. Yes.
Thank you for a nice presentation, which is very, very informative. But I have one comment, maybe a general one. Those findings are data from various African countries. And the question is, to whom the recommendations from the findings? Because every country has its specific complications in issue of modeling or planning health issues. So to whom the recommendations are, or to what extent they can be used at country level? Thank you.
Very, very good question. Yeah. It can be used at different levels. You know, when you start a project, it mustn't always be at the country level. Why should it be country level? It can be county. It can be regional. It can be global. It mustn't be just one level forever and ever and ever. You know what I mean? So what this addresses is at the regional or at the African level. If Africa wants to say, we want to end malaria, that's the policy angle I'm taking. If Africa says, or Africa CDC says we want to end malaria, Africa CDC will have to look at the entire Africa, not even in as much as they are interested in country, but they need to look at the entire Africa. So they will come to you and say, hey, we want to end malaria. What happens if we start by ending malaria from the poorest country to the richest? What happens? You need to show them something. So that's their own policy. So it mustn't always be country or regional or county or province, or it can be any level, but it has policy relevance depending on who is the who can action what policy. Africa CDC can action policy at the globe or the African level. National government of Malawi can action at Malawi level. If you give them that result, they can't do anything with it. So it means it's not for them. So you need to target who you want to target. Yeah.
Yeah. So the concentration index is affected by sample size by any means? I mean, because if we are talking about sub-regional levels, so does it make sense to?
The answer is yes. And I will, that's a very, very, very important question you raised. The answer is yes. And I would want you to read, if you read this up, this thing behaves, it just does its own thing. Okay, it allows me now to do this. I think you should be able to get it from this paper, this one. In that paper, I showed how sample size affects concentration index. Exactly the question you're asking. And it does, but it fizzles out. You'll see the curve. It fizzles out when you max the sample size. It's no longer, it's irrelevant. But at small samples, it is very, very problematic. But at large for large samples, you're good. Yeah, so it does matter, but it fizzles out. Yeah, it's again the law of like numbers. Yeah. Great.
If I could ask you to please summarize in a few words the process of generating CI, that's all. I mean, how do you start with bootstrapping? You do first, and then, I mean, decomposition, how do you arrive at that?
Okay. Yeah, I can do it.
I'm sorry.
No.
But I lost track of it.
The reason why I'm here is to do exactly what you said. So don't be sorry for me. I think it's the next. Oh no, it was before that. Remember, I gave I think I will use that particular slide to talk to. Yeah, this one. So the steps, you talked about steps, correct? Yeah, the first step, compute the concentration index. you can't proceed without first of all computing the index that you want to decompose. First step. Then the next step is knowing that that constitution index can be decomposed into the effect that is due to the constitution index of each factor. Remember, that's why we did the constitution index, elasticity, and then the contribution. So you compute the constitution index of each variable. And remember where we got very high p-values that someone was asking. So the constitution index of age squared, rural, blah, 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 you compute that. Very easy, you compute all of them. Then next, you need to compute the elasticity of health with respect to each age, sex, blah, 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 blah. You need to now multiply this by this to get the contribution. So that contribution we got before called C is equal to this multiplied by that. So this gives us a contribution of interest. So that multiplication. And when you multiply them, of course you sum. Remember, when you sum them up, that's where you get closer to the CI. But to get to the CI, there's something that is missing called the unexplained factor. So if you add the unexplained factor to the sum of the product of these, you get back your CI. And I think he asked the question that, are you sure if we sum up those things, we will get our CI? And then we work backwards, sum them up, we got our CI. So get the CI, get the constitution index, compute the elasticity, add the unexplained factor. The unexplained factor can be gotten as a residual. It's actually, and that's why it adds up. It's like magic. It's a residual, so it has to add up. It's like, it has to add up. So by the time you compute all this, whatever is left to make up the CI is the residual. So it has to add up. It just has to add up. But you need to compute whether it is significant or not. And that is the fact that you just adding up is not just about it, but is it significant? If it is significant, it means it's a part that you've been unable to explain. And I think in that paper that I gave you, for one particular variable, it was significant. And we had to explain it because of the regional and religious differences. Some religions would not allow you to do that, or some regions. Vaccination is a problem because they see it as a sterilization process in Nigeria. So in the North, vaccination is seen as sterilization of their population to reduce the population enough to match the South. So people run away from vaccination. Correct. Right. Correct. Good. Any other question? Happy to. Question? Oh, you still continuing?
Just
okay.
the last thing, like
okay.
The do file that you have shared with us, we can tweak a little bit with our variables.
You can do whatever you want to do with it. I mean, it's out of my hands. It's your property. That's what you get for attending our session. Yeah, and you can share with your students. You can use it for teaching. It's okay. But it will be good to acknowledge where it came from, usually. Yeah, not just, yeah, you know what I mean? Just good science. Yeah. No.
I like this, and I'm just waiting to go back to my hotel room to try to apply your program for other questions, like on HIV as I'm at UNAIDS, and try to see what it gives. On Nigeria, by the way, I have a great data set.
Okay.
On adolescent women and girls,
Which one is that?
Discuss this.
Is the one the seroprevalence?
I have the HIV status, yes.
From DHS? From the DHS?
No. We collected among adolescent girls and women in times of COVID with Monique Kong. You may know her.
No.
She's at Ile-Ife.
Monique, call the name again. The name again.
Monique Upkong Foyaland. Maybe also. Anyway, it doesn't matter. It doesn't matter. Yes, of course, she's my crime partner.
But you work with Matthew units.
Yes, Matt Kavanagh.
Yeah,
Yes.
Oh, okay. I work a lot with him. So
anyway, sorry, it's a family reunion kind of.
Yeah, that's okay.
Okay. I would like to play with your program, which is really great. Now, okay. The first gives the concentration index.
Yes.
Then I have the elasticity for health.
Yeah.
With the second regression that goes in your and then the third one because
Contribution?
Is the contribution.
Yeah. Yeah.
Where is it in this?
Well, the contribution, I didn't put it in, but the contribution is this multiplied by the sum. This is actually, I put it in here, contribution. I think it's my error. Yeah, that line gives you equal to contribution.
So, okay, so I just need to add an unexplained part and then to get the health concentration index.
Correct. Now, let me quickly show you the result. Then you see why that.
Now, but okay, this is the first level of my question. Yeah, I'm slow in understanding.
No.
Then your summation is for each variable of the G.
Correct.
Contributing factors. But what we get from your program is each factor independently.
Yes.
So
independently,
if I want to sum,
then you sum. There's a bracket here. You should have put it more. I would have put it more formal so that you see there should be a bracket here. Okay, a bracket here for people who want to really be technical. Yeah, you get a point now. So this multiply by this for each. Then this sums for all.
So the contribution, the last of the third regression is this sum.
The sum, correct. The contribution of this.
Contributing factor.
Correct. And this also contributes. This is the last contributing factor after you added contributions of all the J's. And this is the last bit, the unexplained. Yeah, thank you.
If there is 4 available, if I'm just breaking down,
then
it will be 1 multiplied 1, then second multiplied second, third multiplied third, fourth multiplied fourth. Outcome will be there, and the unexplained part is the fifth one. And its total sum of
correct.
So among the 4, we have to see that which p value is significant, that is significantly contributing.
Correct.
That's the independent thing.
Correct. Are you getting it?
I'm just.
Okay. Well, now how do you get it on? Explain. Let me go back again. When you do all this, you add them up together. You do this for factor 1, you multiply this, factor 2, you multiply, factor 3, factor 4, you finish multiplying. You add them, 1, 2, 3, 4. You add them together, it will not be equal to the CI. It may, but usually it's not. So the unexplained part is the residual. The residual is now, imagine the concentration index is 1, and this is 0.8. Then we now know that this will be 0.2. The residual. Yes, pretty much.
That is in statistical model, what we do is that some independent variable or contributing variables is contributing, and some external variables are there. We couldn't consider in the model.
Correct.
So that are considered as error.
Correct.
E. That
correct.
E is the unexplained part.
Correct. Yeah. Like religion, I can't put religion, but religion plays a part. Also, some harmful cultural practices you can't quantify. They all. Yeah. Good.
I think some question from online.
Oh yeah, I didn't check online. Oh my goodness, that was an online present. I apologize.
Someone is asking, can online participants also receive the do files? Not sure how that can be done. But
let's take a picture of. Yeah. So, okay, I will explain. If you're online and you can hear me, what you need to do is you go to the QR code, you scan it, or you copy the URL you see there. I think it's down. I will show you in a while. Just patient. The computer is a bit slow. Yeah, you can copy the URL. It's up to you which one you want. I think you can take a picture now as you speak. Take a picture of the URL So if the QR code doesn't work, the URL is sure to work. Yeah, you key it in, follow, just be meticulous. Make sure you put a K is a small K, U is a small U, Y is a small Y. The big Q is a big one, and then 5. I think that's pretty much it. Awesome, thanks. Pleasure. Rabisile. Good. Great. Any other question? That's all? Ah, okay, good. So that was Ebisile. She was actually my student. So that's Ebisile asking that question. Yeah. Great. It's a pleasure for you to have joined us. It's one of the weird sessions, but I'm glad you guys joined. A pleasure. Yeah.